Okay, ladies and gentlemen, time is more than 9:30. Welcome to our ERC seminar in atmospheric sciences. And due to this, that we have this camera and recording, and people can look this also other places, that's why we need to speak to microphone. Is this microphone now okay in your point of view? Good. And secondly, why I have this black hat? This is a European Research Council cap which they just sent me yesterday, and at least at the beginning I decided to use it today when we have this seminar. Yes? They are hearing something, but the microphone is not on. Aha. Maybe we need them to make the change with the microphone. Before I make any bigger problem. This is working, this is not. But why this is not working? Now it starts to work. It was a little bit less tight connections. Okay. We decided to have this. Hey, this is not. How to change the slide? This is not working as it should work. Only with that one. Okay. Altogether in Finland we have got 115 ERC grants, and 11% of them have been applied by our people, and also that we have research get this. And now we have think our people in very let's say liberal way. We count also Paul Winkler as our people, since he has worked with us related to these things what he's doing. It means that since 2008 we have got 4 advice grants, 2 consolidator grants, then 1, 2, 3, 4, 5, 6 starting grants, and 1 proof of concept. The proof of concept you can apply after getting one of the other grants, and then you can also apply some funding for proof of concept, which is actually smaller. But altogether it means that we have got something like 24, 25, 26 million euros with this ERC grants altogether in our research area. And this is actually quite a lot. It's a significant fraction of the funding and what we have received in atmospheric science in recent years. And it's particularly why it's that important. It's more or less free money. You can do basic science with that. There is of course some boundary conditions due to the point that what you are doing, but as long as you are making very good science, excellent, outstanding science, you can in principle do whatever you want. And of course this proposal gives you guidelines what you plan to do. Okay. Now this hat is already enough, like in all dissertations. I will leave the hat there. Today all of us will give the presentation, and the name of my first advanced grant was atmospheric nucleation, and acronym was ATM Nucle. And then let's look first a little bit about the history, why we went to that one. We have seen the first paper on atmospheric nucleation, like we call it in that time, in Hytiala, and it published in 97, more or less exactly 20 years ago from now. And this was actually something which was based on our winter school report. And in that time we have also the first bananas. By the way, we do not have. We cannot use laser when they are not getting it. Okay. Anyhow, we had the first bananas in that time, and they does not look as good as nowadays. At least in some kind of visualization, we have get some improvements during 20 years. And in data analysis, we also made the first data analysis, and already in that time, we find out that it seems unlikely that the condensing molecule X is sulfuric acid, since we simply have too small amount of sulfuric acid in the air that they can make it. And as you see, we started around 3-4 nanometers, the growth. The banana started around 3-4 nanometer. And one possibility is that the growth is caused by some organic acids or organic whatever. And the growth seems to be limited by species with gas phase concentrations more than 10 to 7 molecules per cubic centimeter, and their saturation vapor density below 10 to 5 molecules per cubic centimeter. I think that all this what is now in red is still valid after 20 years. Not very much different. Okay, what is this organic compound? It's still a question mark, and I hope that some other presentations will give more insight to that. And then there was also in 2000 the first explanation that there is something below 3 nanometers. And in that time we called them thermodynamically stable clusters. Right now we might know that they are not thermodynamically stable. They might not even be clusters, but they are certainly between 1 and 3 nanometers. And processes in 2003, also before my first ERC, we were thinking that there is nucleation, initial step of the growth, including nanocovalent and heterogeneous nucleation growth, and of course aerosol dynamics competition between processes. And also about this history part, I will now show you open questions made in 2002 and answers what we had in our hand when I started this my first ERC. And this is already also some history. In 2002 we had the question that how often and in how large areas new particle formation does occur in the atmosphere. And it seems that there is very large areas, continental areas, and it seems to be important phenomena. This was the answer in that time, in 2009. And what happens below 3 nanometer? We can answer that ion spectrometers can show some part of it. And in 2009 there was really not PSM results, neither Apitow or CI Apitow results to show that what are the composition and how this clustering goes on, etc. And we have some idea that we might be able to detect the neutral clusters in detection limit 1.3, 1.5 nanometer. There was some idea that PSM is coming. Then are there neutral clusters? Yes, we had several indications that sub 2 nanometer pool exists, and the composition of nucleation mode aerosol particles. There was, I think, that the solubility things, condensation particle counter batteries, TD SIMS and Apitow, which start to be the first results, first spectra on that time, but not yet in real atmospheric use. More open questions. What are the chemical precursors of fresh aerosol particles, sulfuric acid and biogenic organics, and contribution of ammonia and amines? Pretty similar than today. How much do biogenic aerosol contribute to the tropospheric aerosol and CCN load? And the estimation in that time was 30 to 50% in number, but I think that it's too small number if we use the present knowledge. And related thermodynamics and saturation concentration condensate vapor seems to be around 3 times 10 to 6. Actually, this earlier answer was better than that one. Since this 10 to 5 is, I think that according to present knowledge, better than this 10 to 6. And more laboratory experiments are needed. And when I submit this ATM nuclei, the aims were to quantify the mechanism responsible for atmospheric new particle formation. Okay, it's not quantified during my first ERC time, hopefully during the second, and of course all other 10 ERCs are somehow contributing that. And second, to find out how important this process is for the behavior of global aerosol system and ultimately for the whole climate system. Okay, some progress, but certainly not the answers to those aims. Already in that time, at least to me, people were telling that I need to have this kind of aims which are more or less impossible to achieve during the period. But not too risky. Risky enough, but not too risky. Okay, then I had plenty of research questions. I'm not going to read all of them, but since everybody who wants to get a copy of that one, you can ask me or Anna or Risto to have a copy of it, and you can then read those research questions. But the main questions were that what are the key processes related to new particle formation? What are the processes behind formation and dynamics of atmospheric clusters? How does atmospheric new particle formation affect on the global aerosol load and radiative forcing? And how have the role of biogenic freshly formed aerosol particles changed from pre-industrial time to the present, and how it will change in the future, for example 2100? This is enough questions to answer for next 20 years. And hypothesis was that if we are able to solve this problem, we are able to reduce the uncertainty in this atmosphere global radiative balance in aerosol point of view. And this might be still important. And then the second hypothesis was that the cluster formation is related to biospheric processes like photosynthesis, photorespiration, and that the activation of clusters by sulfuric acid and amines or organosulfates are the key processes behind new particle formation. And of course, what has happened during that time is that we start to work from let's say from nano to global scale, from nanoscale to global scale. And important is of course to find out this new particle formation and growth events, and composition and concentration of precursor gases, initial clusters, gases responsible for the subsequent growth, etc. And as a tools, multiscale modeling, instrument development, remote sensing, besides these atmospheric observations and lab experiments. And if you think about in 2009, just when this ATM nucleus starts, there was a paper by Jonas Merikant et al. On the significance of nucleation on global scale. And if you look this global CN, it shows that already in those calculations 70 to 80% of global aerosol number load is due to nucleation or new particle formation. In CCN, it depends on the how high supersaturation is in the CCN count, but it's between half and 60% what is on CCN load. And this was the estimations based on models. And then during this ATM nuclear, one of those things is that we try to find out data all around the world, more and more data. And of course we do not get the answers already during that time, but now we can see that the continental new particle formation makes something like 5 times 10 to 28 new particles per year. And then there is also background formation, which is coming for my next ERC. which is starting more or less now, which gives also quite high fraction. And then Pauli Paasonen has published this, how much primary emissions are making in this global aerosol load, and we actually see that nucleation, including background nucleation, is making 80 to 90% of new particle formation. And then one very important things what has happened during the last 10 years is this development of new instruments, and I think that Mikko or Mikael hopefully are speaking more on that. But mass spectrometers, particle size magnifiers, ion spectrometers, all of them has been developed more and more during that time. It means that we are now able to discover the world below 3 nanometers. And for example, when I was looking this ATM nuclear proposal, there was no mention about CI-Apitow, very little mention about PSMs, mainly saying that maybe something can happen with those, and mainly relying on ion spectrometers, which means that during the project almost everything changed since after these 5 years. Not a little bit, quite much independent of what I was doing, but anyhow, what was happening inside our group is that we had more and more accurate measurements, which still has a lot of work to do, but anyhow, some things were related to those. And if you think the present understanding on atmospheric clusters, the theory and predictions and experiments existent for atmospheric clusters predicted 2000, they have found certainly during the last 15 years. Concentrations predicted around 100,000 to million, but the concentration seems to be much less. Several observations, and still thinking that maybe something is missing. And like Mikael said in one discussion, that maybe I have ate too much mushrooms to see that there is a million, although observations of only 1,000. 3 orders of magnitude difference. Size-dependent growth seems to be all around the world, and very extremely low volatile organic compounds was predicted in practice in this 98 paper and found later on. Then a little bit about gas-to-particle conversion, since now the newest ERC works with atmospheric gas-to-particle conversion. With starting with chemical reactions to make extremely low volatile compounds clustering, and then also activation of those clusters by next vapor to get enhanced growth, and then multi-component condensation on growth things. And if I now look the idea, my main aim is already quite different. Now this main aim is to attain a deep understanding of something, not anymore to solve all those issues which are hard to solve. And the main thing what I'm looking in that one with the people who are working there is, first of all, to find out that why there is so much new particle formation in Chinese and other megacities. In principle, there should not be. There is some chemistry, some nanophysics going on which we don't know. And secondly, why there is so little in pristine Siberia, in pristine areas, boreal and Arctic areas, why there is so little of those. And third one is that how this nano gas-to-particle conversion will affect on this continental biosphere aerosol cloud climate feedback loop. And if you look at the present understanding, how I see it, we see that sub 2 nanometer mode there's always sub 2 nanometer mode, at least ion mode, quite often also neutral clusters, but it's very hard to grow them from 2 to 4 nanometer. Then ion-mediated nucleation seems to be more important at these cloud experiments at CERN than in the atmospheric condition. Reason seems to be effect of recombination. New particle formation seems to make 75 to 50% of the global aerosol number load in planetary boundary layer. And if we take into account the free tropospheric contribution, it's around 90%. But mechanisms are still a little bit unclear. And as I said, why we do see new particle formation in heavily polluted megacities. Why this is a question, why there is a very little new particle formation in Siberia, and is it represent a very pristine clean environment, importance, relative contribution of different processes, different mechanisms, and interactions between boundary layer dynamics, new particle formation and pollution. Those 4 bullet points are the main things what I'm doing right now, and also during the next 5 years in my ERC. Okay, thank you. And the idea is that after all presentations, every presentation we have time for 2 or 3 short questions or comments maximum. And since we are recording them, Anna will give the microphone if somebody is interested in. If not, we can also move on to the next presentation.
Any questions, comments? No? Not at this point?
Okay, and next one, if I remember correctly, is Sergei.
Just use the microphone.
Mm-hmm.
Yeah.
So I had two ERC projects. One is advanced and is called Atmospheric Planetary Boundary Layer, Physics Modeling and Roles in Earth Systems. So the goal of the project was to, or ambitious goal of the project was to revise basic theory of planetary boundary layers in view of new evidence of uncertainties and inaccuracy of the basic turbulence paradigm underlying theory of geophysical turbulence and theory and then parameterization of planetary boundary layers. And practical motivation was that in atmospheric models, all parameterizations were, and frankly still are, based on rather old-fashioned physics, which is already to a large extent revised. So it was 2 goals, to revise the theory and, well, to make first efforts towards improved parameterizations and models. So the basic word, the key word is turbulence. And turbulence, everybody knows what is turbulence, and we hear it many nowadays in very different contexts, not only in scientific but in political. People are saying of turbulent policy or turbulent economy or like that. Actually, but what is important that even in physics there is no strict enough formulation what is turbulence. And one of the important features of turbulence is that this is not simply chaos, but multi-scale chaos. And perhaps the first person who emphasized this in his short sentences at his drawing of turbulence was Leonardo da Vinci. He several times mentioned that there are different eddies from big to small, and this is indeed important. Actually, the concept of spectrum underlies the modern theory of turbulence. An important issue is that there are big eddies and the small eddies. And Richardson was perhaps the first who realized that big eddies break down to create smaller and smaller and smaller eddies, and the final goal of the smaller eddies is to convert into the molecular motion, that is to temperature, and this is dissipation. And then Kolmogorov quantified this idea. And his quantification was, frankly speaking, he was not a physicist and not a, but he was a physicist, but he was not an experimentalist, and he created his idea of turbulence, quantified the cascade from larger to smaller eddies by analogy with a moving of stones over the very, very long slope. The stones collides and break down. And then at the end of this process, there is a sand, no stones. And importantly, the stones, once broken down, never reassembled. And this was the idea. And this is called, how does it called? It was direct or forward energy cascade, only from larger to smaller eddies. This is important because, and Kolmogorov's views dominated the theory of turbulence since his first formulation in a couple of very short papers, by the way, in 1941, long ago. And until the end of the century, his ideas dominated the theory of turbulence. But Kolmogorov considered, he published his paper and applied his ideas to very, very simple type of turbulence, to shear flow, to boundary layer flow, neutrally stratified, which is very important and typical of engineering application over the wing in particular, and in pipe flows and so on. But it is not strictly applied to atmosphere, to geophysical and astrophysical turbulence, to atmosphere, because in the atmosphere we always deal with stratified flows, either stable or unstable. Neutral are very rare. But the influence of Kolmogorov's ideas was extremely strong, and all theoretical ideas until recently are based on the Kolmogorov vision of turbulence. So what happens then? And then we faced more and more difficulties. As a matter of fact, we are now observing the crisis of Kolmogorov vision of turbulence, because it is not satisfactory in many cases. In convection, we have merging plumes instead of breaking eddies. And when convection starts, at first originate small-scale uprising plumes due to buoyancy forces. And these plumes have no tendency to break down, but rather merge to create larger plumes. It is totally different, and so on. This is unstable stratification. In stable stratification, another difficulty. In stable stratification, laboratory experiments and classical theory of hydrodynamic instability resulted in a very simple and straightforward results. If the static stability is not very strong, below so-called critical Richardson number, then shear generates turbulence. Boundary layer flow is turbulent. But when the static stability is larger than some critical value, then flow inevitably becomes laminar. And this is confirmed by lab experiments and was considered as a very big achievement of the theory, because hydrodynamic instability and generation of turbulence both provided one and the same threshold, critical Richardson number. And this critical value is 0.25, you see, so it's very small. But what we observe in the free atmosphere or in deep ocean, Richardson numbers could be up to 1,000 compared to 0.25. And at the same time, turbulence is ever present. So this was a puzzle, and this puzzle also is indicative of we don't understand something. So now I will show how different types of turbulent flow look like very fast. This is engineering, which is very good for the Kolmogorov vision. Engineering turbulence, and you see here big eddies, you have small eddies, and well, this is so-called shadow photo, and you can see in this shadow photos how big eddies break down strictly according to Kolmogorov vision, like colliding stones. And this is geophysical turbulence. Geophysical turbulence look very different. Here we see boundary layer with a very, very strict upper boundary, very stably stratified, and even more stable stratification above the boundary layer. In both cases, we have turbulence. This doesn't look similar. And this is convection. And in convection, we see how turbulence, this is observations by from the airplane over the desert, and this is turbulent flow where turbulence is basically generated by buoyancy forces. And we see here in these observations that convective turbulence have a tendency towards self-organization, and from small plumes eventually generates a large-scale flow with the sizes of several kilometers. And we see here uprising plumes surrounded by downdraft, and we feel this self-organized flow as just a wind. So it is this observation contradict to Kolmogorov's idea of only forward energy cascade. This is inverse energy cascade. This is also, you see how order from chaos. We have two kinds of movements: chaos out of the order, this is Kolmogorov vision, and order out of the chaos, which is Prigozhin's vision. And we see this is another illustration how convective turbulence looks like. It looks very different, and these are uprising plumes rather than eddies. This is once again, people call it turbulence, but this is turbulence with only 2-3 modes. So this is not multi-scale, it's monoscale and, well, a few scale. We prefer to call it nowadays pre-turbulence. This is not turbulence. And here is just illustrations that turbulence is everywhere, and Van Gogh saw the world as very turbulent and reflected it, this vision in his paintings. So all these issues were the subject of the project, and the project resulted, well, it's not resulted in discovery, but in clarification of the understanding of boundary layers as a key elements of geosystems, of Earth systems. Boundary layers, first of all, couple geosphere into interconnected climate and climate biosphere system. I tried to show this in the diagram. And importantly, that boundary layers are the most turbulent parts of the Earth system. And most turbulent is most comfortable for life, because much more than 90% of the life is concentrated in boundary layers. This is important because it's delivery of the nutrients in the ocean, also for microorganisms and so on and so on. So this is we need chaos. Chaos is an inherent feature of the word comfortable for life. The function of turbulence, boundary layers, and surface fluxes in climate system and climate biosphere system. We had one small step forward. The traditional view was that linking the atmosphere and underlying Earth surface is fully characterized by the surface fluxes. Not necessarily, not only turbulent, but turbulent to a large extent. And I tried to demonstrate it as this, well, bottleneck bottleneck is just a limited turbulence in the close vicinity of the surface. It's make a boundary. And traditionally, it was considered a major boundary. And if we know the fluxes at the surface, then we know the interaction between the atmosphere and the Earth's surface. The theory underlying calculations of surface fluxes is one of the major achievements of the Russian school, the well-known Monin-Obukhov similarity theory, or MOST, M-O-S-T, MOST. And at the moment, until present, all flux calculation schemes in operational modeling of air-water, air-land interaction, weather prediction, climate, and so on, schemes are virtual and reality in the Monin-Obukhov similarity theory. This is not surprising because the theory is based on the Kolmogorov vision of turbulence, and as I told you, Kolmogorov vision of turbulence is not always correct. This is first. And second point is perhaps even more dramatic. I missed it. Second point. Okay. Then I say it by words. The second point is that besides the boundary at the very surface, we have one more boundary, the upper boundary of the boundary layer. And the upper boundary of the boundary layer, once again, create a difficulty for properties to penetrate from boundary layer to the free atmosphere because of very stable stratification on top of the boundary layers. And this makes the atmosphere essentially consisted of two parts, boundary layer, well mixed, and bounded from the surface, from below by the Earth's surface, and from above by this very stable with the density jump, which prevent immediate penetration of properties upward. And this is very important, becomes very important. Until recently was not, practically not needed for meteorology because very low resolution modeling. When low resolution modeling, then local features were anyhow impossible to resolve. But when we are capable of resolving local features of weather, climate, and Earth, and the Earth's surface as such, then the role of the upper boundary has become very important because it is precisely due to boundary layers that we have very variable weather and climate. At short distances, we can have very different air quality and air pollution at neighboring streets in particular. And this is controlled to a large extent by the upper boundary. So we did that. So this is once again illustration of the role of the boundary layer. How much time do I have? Very little. Okay, then I will proceed further only with illustrations. This is how convection is self-organized. It is self-organized in two types. In the form of convective rolls, we always see it when flying, and convective cells. This is another kind of picture. And this is the same observations which I show you, that this is self-organization. And what follows from the self-organization is a dramatic increase in the heat transfer. Thanks to self-organization, we have convective winds, which classical theory don't see. And convective winds produce very strong mixing at the surface and could enhance heat and mass transfer up to 10 times. And this was missed until recently. Nowadays, it's included in models. And this is another, I don't know how to switch on, movie here. Click here. Yes. And here, how the upper boundary of the boundary layer, how acts on air pollution. This is, of course, this is a picture. This is not observations. If we have a deep boundary layer, then everything which is emitted distributed over deep layer, and that's why the concentration is not very strong. But when the static stability increases in the night, then the boundary layer goes down, and the same amount of emitted material is concentrated is spread over shallow layer, and then the concentrations become much larger. Of course, this is very important for air pollution. So we did a revision of the classical paradigm, and shortly it's as follows. The Kolmogorov vision was that only from order to chaos. This is from order towards this chaos, and never other way. But in reality, it could be both ways, from order to chaos and from chaos to order. So we need, and we did it, to include these features of turbulence in modeling. This was a first project, and then the holders of ERC grants were invited to make a kind of commercial application, possible commercial application from the project. And I attempted to do that, and my project was funded. And the idea was that nowadays, equipped with new vision of turbulence and boundary layers, we can much better understand and prospectively numerically simulate and model local features of microclimate and local weather. And of course, this is a strong demand from the society. So, in particular, we have strongly heterogeneous conditions in cities, and especially in megacities. And then what is needed in order to create new services? Okay, new services addressed concrete client. Different people need different issues, and of course, National Weather Services can answer each question. It's a problem for private services serving for concrete clients. So we have created such a business plan, the idea and business plan, and it was strange enough, this is for the first time in my life where I was involved in creation of the business plan, and I was absolutely unsatisfied with our result. It was one-year project, but surprisingly, the chair of the Proof of Constant Commission called me and asked whether we can meet, come here to speak to me, and it happens that my modest project was considered as one of the best, if not the best. Anyhow, no business emerged from that, but anyhow, so it encouraged me to go on thinking about possible business applications. Here is just a picture of air pollution, and this, I think, is important. This is numerical simulation demonstrating how different could be air pollution even in neighboring streets. This is from Alexander Baklanov project Megapoly, numerical simulation by Nuterman. This is another picture showing strong heterogeneity of air pollution, and I'm just recalling that boundary layer issues and practical application, including personal environment, are a contribution to what we are doing in the scope of Pan-Eurasian experiment in response to grand challenges. Here are the grand challenges, and I marked with red the challenges in which boundary layers play an important role. Thank you for your attention.
Okay, thank you, Sergei. Keep our schedule. We need to move on. Next one is Hanna Vehkamäki. And then after Hanna, we will have Ilona Riipi. And why somebody has 20 minutes is due to the point that they have 2 ERCs. That's why they have 20 minutes.
Okay. Here are the titles of the 2 ERCs. If you're wondering about my age and career, etc., there were no consolidator grants at that point, so I the present starter and consolidator grants were just one grant, and I got this, I mean, in the starting grant at the stage where I would have been in the present system consolidator. So as you see, it's about molecular clusters, and it's all about theory, and it's basically computer-assisted theory, and has always been. So this was kind of the idea, or the sort of mindset in the beginning of my career, and just before this, I got the first grant. So the experiments had traditionally reached down to 3 nanometers. So there is the size of the aerosol particle on the x-axis, and the experiments kind of stopped at 3 nanometers, which was already kind of revolutionary. Those bananas were observed when that sort of instruments were developed. But then there were some instruments as well which could detect molecules. But then there was this kind of mid-ground where actually the sort of, I don't say nucleation because I'm not so sure it's nucleation. It can be completely barrierless, and it can be just like a chemical reactions. But where the key phase of particle formation happens somewhere between 1 angstrom and 3 nanometers, there were not really any experiments observing those, but what was worse from my point of view, there was no theory. We could somehow model single molecules or maybe 2 molecules together with quantum chemistry, and then we could model something like 3 nanometer or 10 nanometer particles with thermodynamics. But in between there was this sort of trouble region which we couldn't attack with kind of either experiments or theory. And what then happened is that mass spectrometry developed so that it could be applied effectively to aerosol precursors, the gases, and also the small clusters. Also, PSM was developed, which pushed the mobility analyzers, the cutoff size of the mobility analyzers down. And also, what was kind of my point in the first ERC is that we wanted to follow that development, the experiments in the theory, and be able to do some decent theory for those clusters. And what we did was we did quantum chemistry for these small clusters, spend a lot of time searching for methods that could do some sort of reliable job on these clusters that are fairly big for quantum chemical methods, and then just build a model that basically didn't use the thermodynamics at all, but treated the clusters up to a certain size with quantum chemistry, and see whether we can in any way match the results from the much improved experiments. So I want to say now that you're wondering, well, if we achieve that, what next? So I want to say now that in these models that we used and still use, all the cluster properties are based on the idea of equilibrium. So the cluster has found its minimum energy or minimum free energy configuration, and that the properties of that configuration are used to describe the cluster. And then we kind of deduced the collision rates between clusters and molecules, and we deduced the fragmentation rates of the clusters from these quantum chemical calculations. And then we see how the cluster population evolves in time, how the clusters grow, and then we see what we get. And this is kind of the problem setting, is that we have sulfuric acid concentration on the x-axis, then we have particle formation rate as how many particles are formed per cubic centimeter per second. And this is data from atmosphere. So to understand what is happening in the atmosphere, we should get with that sort of 10 to the power 6 sulfuric acid molecules per cubic centimeter, we should get about 1 particle formed in cubic centimeter per second. Then there are some laboratory experiments from cloud, which we compared with, and those black triangles are sulfuric acid, ammonia, water mixture in the cloud chamber. And you can see that the theory, which is the line, there are huge error bars, which I don't bother you with now, but the theory kind of nicely fits both the trend and the magnitude. So at least we are in the right ballpark with the theory. And here there is a little cluster of 2 sulfuric acid and ammonia, just to remind you of what stuff this is. Okay, theory and experiments match, but this clearly has no atmospheric relevance, because with 10 to the 6 you get something like 10 to the minus whatever 8 particles per cubic centimeter per second. So the formation rates are far too low with this. And then if you put, instead of ammonia, you put DMA, which is a little bigger molecule there, again joined with 2 sulfuric acids, you see that both the experiments and the theory, the results jump up. The match between theory and experiment is not so great, but it's not bad either for particle formation studies. And now we get some sort of, with 10 to the 6, we get somewhere close to 1 particle per cubic centimeter per second formed. This doesn't mean that I claim that DMA sulfuric acid is the only one mixture forming particles in the atmosphere. That's not the case. We know that there is too little DMA. But for us, this was a great news, because this was the first time we could in any way get the right magnitude of formation rates with the right amount of sulfuric acid. So it kind of tells us that this kind of compound we are looking for. And computer simulations are maybe not as expensive as experiments, but they are so expensive that we can't just go through all the possible molecules that there are in the world. So it was a kind of great thing that we managed to hit one nail that seems to go in, rather than, you know, some rubbish that is interesting itself, but clearly cannot even conceivably have any atmospheric relevance. Okay, well, of course, we would like that blue line to be exactly on top of the blue points, and then, of course, we would like to have something that is measured in the atmosphere that could explain the atmospheric particle formation with the concentrations that have been observed. But apart from these minor little tweaks, what's left then? How do you convince ERC to give you another grant to study this? Well, that's by saying that A, there is a problem, that we don't exactly understand what's going on. But I would say that what became clear in this process, that, and this is not to say bad things about the experiments, this is to say that this process is pretty complicated, and we don't exactly understand what those experiments are actually showing. We don't know what is measured, what are the clusters exactly there, how many of them break in the instruments. So what is the relation between what we see after the instrument, I mean, what the instrument kind of shows, and what was originally in the atmosphere. And the other two, actually I'm going in a funny way. So let's go this way. So I guess the central selling point of this second ERC, which has just started, is to try to understand what happens to the clusters in the instrument. Because the clusters, when they are first chemically ionized, then they go through these lower and lower pressure chambers, this atmospheric pressure interface. They lose molecules. Well, they can also gain molecules in some cases. But they lose molecules through different processes. And what we are actually detecting, or what the experimentalists are detecting, is not the same guy that went into the instrument. And to understand why we do not exactly match the experiments, and also to get much more information much more detailed information from the existing experiments, we need to understand that stuff, what's happening there. And the problem now with those clusters in the very colliding, because they are going very fast, because they are accelerated by the electric field inside the instrument, they are colliding very hard on the remaining gas molecules inside the instrument, plus there is no thermalizing gas, or there isn't enough of thermalizing gas, so they are not in equilibrium. So we need to understand what happens, how the clusters behave when they are not in equilibrium. Are they fragmentation rates, for example, much, much larger when they are not in equilibrium, or are they ballpark the same as those equilibrium clusters that we know how to treat? And that's the one thing which we don't kind of have this sort of meat mill methodology that we can just take and use. We have to search and develop methodology to treat the non-equilibrium side of things, to understand the clusters inside the instruments. Also, nucleation or particle formation in itself is a non-equilibrium process. We don't know whether that matters, but like inherently it's a non-equilibrium process because something happens. In equilibrium, kind of nothing happens. So we don't know how much it matters to the description of the process itself, that those non-equilibrium effects. And then there is one other thing that we have started to do, ice nucleation. So not only molecular clusters forming from thin air, but also ice forming on substrates. So there is a substrate, some aerosol particle, and then water molecules are forming ice on top of it. And this is kind of new thing which we did not model before this second ERC. This I showed, and then I finish with a current collection of people who are doing this. And I don't have any results from the second ERC yet. It started less than a year ago. But I have collected some good people, and a couple of new people will join in a few weeks. So I would say that the recruitment phase is not completely over, but the major effort to find people is over, and now we are kind of ready to really start working. It takes about a year to gather new people if your, how do you call this, pajazzo is completely empty. So all the people have left, and you thought you have no money in the future, and you have made sure that those people, find jobs elsewhere, and then the ERC lends you a load of money, and then it takes ages to find decent people. So I'm not complaining. I'm just pointing out that there are these sort of first world problems. That's all.
Thanks, Hanna. We have Hanna's presentation that short that we have time for one or two comments. If somebody wants to ask something. If not, then we move on, and Ilona Riipinen is the next one.
Yes. Yeah, so good morning, everyone. And thanks a lot for the invitation to come here. It's nice to be in this group, and indeed very impressive to see so many ERC grants granted for the sort of Finnish atmospheric science community. So I will kind of go one scale up from Hanna's presentation. So my project has also been mostly about modeling and theoretical work, but not so much on the really molecular scale. But looking at gas-particle interactions and condensation and evaporation especially. What else should I say? Yeah, and maybe kind of as an outline, I think besides showing you some highlights of the results that we got, I also have quite a few slides about just what we did with the money, why I applied the grant, and what kind of impact we had. My grant, by the way, what was called Atmogain, is also already, this project has already ended. So it was between 2011 and 2016, so all the reporting is done. And I'm a little bit different, I think, from many of the ERC grantees in that sense that I still haven't applied for my next consolidator grant because I'm really working on the concept, but maybe in the future. Okay, and I thought I'd start from a personal perspective. So why am I interested, or how did I become interested in gas particle interactions, besides working on at this Center of Excellence here? Well, I think I've always been fascinated by large systems that are made of small parts, and kind of those larger scale behaviors or phenomena that arise from interactions in the small scale. For instance, like how molecules make up aerosol particles or cloud droplets, or how these droplets then make up clouds or cloud systems. And in these kind of systems, well, first of all, I really always liked thermodynamics and statistical physics when I studied. And I think these kind of scaling problems are fascinating. How do we, for instance, represent these small-scale phenomena in, say, climate models or air quality models in a way that kind of appreciate the molecular level but still are simple enough? And then I must also say that one reason I think I have decided to work on the topics that my project was about was also related to the relevance that it actually, kind of in the back of our mind, we can always say that what we do provides something that hopefully will be useful for the humanity. Okay, and then I also thought I'd engage a little bit of the human in you, although maybe this is all very clear to you, but why should you care about gas aerosol interactions? Well, I mean, you might be curious, so you might just want to understand, for instance, how clouds are formed because they are present. I mean, we all see them every day. One thing that's very kind of timely at the moment is that we also have to, as a humanity, I mean, we have to figure out what do we actually have to do to, for instance, meet the goals of the Paris Agreement. And to do that, we have to understand the climate sensitivity. And to understand the climate sensitivity, we have to have an understanding of how aerosol concentrations and clouds have changed during the industrial period. Okay, so you might not care about the climate, but maybe you care about your health or the health of the ecosystems. Or you want to make money by using, for instance, some new nanomaterials. And I think also I decided to start a little bit on this more general perspective, and I thought I'd also kind of advertise the type of impact that the ERC grants can have besides the scientific citations or papers that we publish. I think we grantees should also be active in outreach. So if you're interested in some of my thoughts on linking health to climate and trying to motivate also other people to think about the air and the atmosphere, go and see this TEDx talk. Okay, and then to more about the science. So as I said, my grant has already ended. And kind of one of the overarching themes was related to the scaling. I wanted to address knowledge gaps that were present at the time when I started that were in different scales. So kind of the smallest scale processes that my grant looked at was related to kind of really fundamental phenomena of how molecules stick to aerosol particle surfaces and how do they leave those surfaces. And this it was manifested specifically in this coefficient called the mass accommodation coefficient that we used molecular dynamic simulations to look at. Then the second topic was related to what Markku was already talking about, organic compounds and how they condense and evaporate from aerosol particles, and what are the really fundamental thermodynamic properties. And both of these sort of combined address the general question of how does material actually change phase in the atmosphere. I chose mass accommodation coefficient because that was like a fundamental coefficient that was still under debate and still to some extent is, but much less. And then I chose to focus on organic compounds because they were the group of compounds that were at the time kind of a hot topic, poorly understood, complex mixture. I mean, we still have a lot to learn, but maybe a little bit less than when I started. And then I also wanted to have this element of relevance. So I also wanted to have an element of taking the molecular, smaller scale level understanding and at least testing the sensitivity of, say, air quality or climate models to these phenomena. And especially I focused or wanted to focus on number concentrations of ultrafine particles because they are still much more poorly understood as compared with this PM1 or PM2.5 if we think of air quality models, for instance. Okay, and then regarding the team and the approach, I mean, scientific work is also always about the humans. And like I mentioned, one of the kind of overarching philosophies that I had was that I wanted to have the different scales communicating with each other. And these in practice meant different people focusing on different scales, communicating with each other, present in the same group. And this is what I think, from our perspective, the ERC really made possible, that we were able to have a critical mass of people working on different scales. From the molecular, through the microscale, to the cloud scale, and finally to the regional and global scale. And these were the 16 people, I think this is 16, but this is only 14. These were the 14 people involved in the project. Yeah, I've forgotten myself, I think. I was also involved. Maybe there's one more person missing, but I actually don't think. I think we were 15 in total that were kind of involved in the project. You can also see that there was a collaboration in form of people, exchange of people, and even Taina Ylijuuti and Silja Häkkinen, who were here with the University of Helsinki on one hand, as well as Elhan Baranizadeh, who on the other hand was at the University of Eastern Finland. So there was a lot of overlap, or has been a lot of overlap between us at Stockholm University and the Finnish Center of Excellence. And I would also like to point out that we were quite a balanced group, so that we were about half women, half men, 8 different nationalities, 4 different continents. And then the last highlight that I always like to say is also that these people during my project, besides producing nice science, they also produced 6 babies. So we've already also taken care of the next generation of scientists. Okay, and then I'll show you a few highlights of the research. So in total, we published about 60 papers on these different topics and received about 3,600 citations to these papers. So we were reasonably productive, and hopefully, of course, we will make a difference in the future as well. But the first kind of highlight that I wanted to show was related to the work that we did on the sticking and this so-called bulk versus surface accommodation of both organic molecules as well as water. And what we found from the way that these phenomena had been looked at before was that it actually played a role what people thought about the surface, and it made a difference whether you account for the separately for the sticking of the molecules to the very surface, or whether you actually follow the system long enough to see whether the molecules get accommodated into the bulk. And what we're doing right now, I mean, during ATMOGAIN, we looked at liquid water and organic compounds, but at the moment we are extending this work very much like what Hanna is doing to ice surfaces, and developing the cloud scale models that we are developing at Stockholm University, and looking into the sensitivity of these models to the surface and bulk accommodation phenomena. Then the part of AtmoGain that maybe has made most immediate scientific impact in the form of citations and interest, and has a lot of interface to the work that Markku is doing, Mikael is doing, and many of you, I think, in the audience are doing, are related to the atmospheric organic compounds. So what we did was that we took experimental data from Hyytiälä, from the field, also from the laboratory, and at the time when we started to look at this, we kind of combined the knowledge from a lot of smoke chamber data from the organic aerosol community in the US to what we already knew from our observations in Hyytiälä. So for instance, what we knew about this organic compound X, or this compound X that was growing the small particles. And what we found was that there was a discrepancy, so that the way that people had looked at smoke chamber experiments on secondary organic aerosol formation, they were missing a large fraction of the really non-volatile, very low volatility species that our data from Hyytiälä, or the data from this community from Hyytiälä, clearly showed had to be there. And this was really something that we tried to convincingly argue for, that there had to be organic molecules emitted from the forests, or originating from the forests, that are much stickier, much lower in volatility than people expected, just based on the smoke chamber data. And then, based on this observation, what we did, we tried to kind of develop some kind of a theoretical framework of how these molecules might end up in particles. And now we know, thanks to the work that Mikael, for instance, has done, and I'm sure will show, and others, now we know that a lot of these molecules are made in the gas phase. But in our work, we also suggested, or tried to sort of systematically outline what are the different possible pathways, including particulate phase chemistry, gas phase chemistry, and maybe even some effects that are just related to kinetics that might explain these very kind of sticky organic molecules. And then I just wanted to show some of the interfaces of this work to the work that you are probably very well aware of. So, for instance, Mikael's work, there's a very nice interface to the work that we did. The cloud chamber has recently looked at a lot of these so-called highly oxidized organic molecules, or ELVOCs. We also did some work with a collaboration grant between the ERC and the US National Science Foundation, with Professor Akuya Asawuku's group at UC Riverside, who have a really big smoke chamber facility there. To look into new pathways of forming these extremely low volatility organic compounds. And then the last highlight that I wanted to show was, I think this is the one that has most interface to Hanna's work. So Hanna was talking about these kinetic and quantum chemical models to look at the clustering and evaporation of small particles and the first steps of new particle formation. And what we did, as an example, I mean, this is just one of the examples of the larger scale work that we did in my project. We took Hanna's models and used those to create lookup tables to implement new particle formation in an air quality model called PM-CAMX-UF. And the reason why I would like to argue for this approach is actually that if we really want to predict what happens in the future, if we want to extrapolate to the future or extrapolate to the past where we don't have data, I think it's important that the parametrizations or the approaches that we use in these kind of large-scale models are actually based on let's say, best possible physical understanding that has the best possible dependencies on environmental variables. And there I think having actually like how would I say, like real theory instead of just parametrizations, semi-empirical parametrizations, is a good way to go. Of course, hopefully evaluated with experiments like these models have. Oh. And then as the last slide, I just wanted to highlight what difference did the ERC grant make. Well, I mean, this probably goes without saying, but for everyone, we know now more about the air surrounding us, which means that we have better common sense. Hopefully we diffuse it to the society around us, and hopefully are able to make better policies. Then we of course made a difference for the scientific community, which I already referred to, you know, the citations and papers and all that. For the research environment at Stockholm University, ERC made a big difference because we were able to create a critical mass on a new topic that was not really present in the environment before I went there. And this is also, of course, also a fuel for new collaborations, which we are now really trying to, or are starting to show their fruit when we're working more on the topics that are already or were already strong in Stockholm when I came, like for instance, this cloud scale modeling. For our team, we, of course, this is great advertisement, visibility and good future prospects. Many of my team members who are not with me anymore have got really good jobs. And for me, it made a world of a difference. It really gave me a possibility to pursue what I wanted to do in a new research environment. So with this, I mean, I think we should all wish ERC a happy anniversary. I think it's been a really successful program, as you have probably seen, and thank you for your attention.
Thank you, Ilona. Time for some short comments or questions. One should now remember that after coffee break, coffee is outside there, we will have panel discussion where all our ERC audience will be in the front, and you can ask whatever maybe you are sharing the session. Yeah. You might have some good questions for us. But I think that this, please take your summary. I can now make a question or comment if we don't have copy yet. To solve this, what the difference is ERC making, I can actually say some comment on our Center of Excellence point of view. Without this ERC grants, we would not be at all in this position in Finland, in Finland science. In Finland science environment and research environment, it would be much less without this ERCs. And it's actually very good summary what you have made on this impact, and we should actually make one this kind of set of slides to show this also to our rectors, etc., and our Ministry of Education, what these ERCs are doing for us and for the whole science. But so far, okay, we are continuing after 16 minutes. We can have a coffee during that time.
Okay. And by the way, if you want to communicate some specific questions to me already during the coffee break for the panel, you can approach me. But there will be opportunities to ask also during the panel.
Joni, sanotko siellä kavereille, että tuolla sisältö kahvia? Puuttuuko meiltä joku paneelista? Meillä on täällä pikkasen ylimääräisiä tuoleja. Nenne.
Okay, so all the ERC grantees who are in the room,
Nenne. Jos on tuossa
please join the panel. I think Hannele is also.
ehkä lähti muualle paneelin näyttää, tiedä missä on paneelissa.
Mm. Okay, so I think we can then start. If some of you see Hannele coming to the room, tell her that she can join the panel as well. So okay, so we have 25 minutes and we have 8 panelists. So it will be a few minutes. If everyone says something, it will be a few minutes per each panelist. So panelists, please keep this in mind when giving your contributions. So what I thought, the type of questions I could ask the panelists so we could discuss here is the motivation to apply, advice, who would you recommend to apply for the ERC, and also advice for people who are considering applying for these grants. So your experiences of the application and the evaluation process. And then also what kind of support you have received or would have wished to receive from the university or your surroundings in the application process and after. So the panelists, you can prepare to think about these kind of questions. And then I think in the end we'll try to reserve a little bit of time also for the audience to ask some questions if you have some in addition to this. Maybe we can start by just hearing your reflections about who would you recommend to consider applying for an ERC grant and what motivated you? Yeah, we can make a short round, just a very brief one.
I didn't expect to be the first one here. So maybe what motivated me to apply for an ERC grant was just a number of great examples in my nearest scientific neighborhood. And this included, of course, Marco and this prestigious group of excellent atmospheric scientists here in Helsinki. And then, of course, it was basically also a matter of survival strategy, because if I were planning to stay in science and having a permanent position at some university, preferably in Vienna, I would need some big grant to get funded. And eventually it was successful, and chances are high I get a permanent position soon. That's one of the main reasons for me to apply for this grant.
Yeah, also my, of course, strategy to stay in science. I thought that it's kind of necessary to get some funding. It's also considered as kind of duty. I'm working here, and one of my duties is to keep this system running and contributing, getting money here. Well, and when I first time was applying ERC, I was motivated by the thought that I knew that there is a slight possibility that I will get it. Second time, when I was applying after first rejection, I was still kind of thinking that maybe there is a slight possibility. And third time, I was just so bored in the whole thing and pissed off that I thought that I will apply until the end, and independent if I get it or not. So, and then I finally got it. So, yeah, I don't know what to say more.
That was a perfectly fine answer.
Yeah, I guess I agree with the other speakers, and also it's a survival strategy to get funding to begin with. But of course, it's not hard to find reasons to apply specifically for the ERC, because the ERC, of course, gives, like Markku said, this very free money also that you can then really try to go for your own direction. And it does indeed give you quite a lot of freedom also. And somehow, as I saw later on, that it also, you start getting invitations to events that you would not get beforehand and stuff. So it does kind of, people know the ERC grant quite well by now. So it is, it's a very good step forward to actually get it. So I would recommend to really to try to apply for it for anyone who even feels a remote chance of getting it.
Okay, in my case, of course, getting this great funding was one of the motivations to apply it. But why I wanted to apply it to my specific topic was that I felt that I had pretty well-defined, specific scientific questions that I wanted to find an answer to. And I also felt or believed that if I get the funding, then the results and my research would make an impact to my field of science, which is atmospheric aerosols. And that was, I think, one of the major reasons why I thought that I had chances to get an ERC grant. And I think that your second question was that who we would recommend to apply this funding. So I think that it's mostly about the idea. So if you believe that you have very good idea which would have impact on your specific field, then I think that you should apply funding.
Well, so I would share my experience also in getting and being rejected. And I would say that I strongly encourage people to apply, because I think it's they have very, very good rules. I was involved in a commission for consolidation grants and took part in meetings and so on. It's a very, very friendly atmosphere, and then it's very good to have a very clear rules. The rules are simple. It must be quality of research, nothing else. And this is very good, quality of research first. Second, I got not only accepted, but was rejected. And I fully agree with the rejections. The last time I applied together, Markku got the second ARC, which is very difficult. Because the rules are as follows. It shouldn't be just extension of the first. It should be something new. And I got criticism which was shortly, this is not new topic. This is just further extension of what was done in the first ARC. And it's difficult to reject. That's why I think it's a best way to the easiest. For me, it's the easiest. So I encourage people to do that. That's easier to any other, in spite of big competition.
Well, I guess most things have been said. I feel that one of the big motivators was that it gave me peace to do something and not just write applications all the time and try to look for, like, small pieces of money and small things and quick collaborations. And it gave me peace to do whatever I wanted to do or whatever was my vision for a long enough time that there was really time to kind of build the momentum and go into the depths. And I don't know about other people's sort of guts, but I think it's not about tactical tricks or stuff like that, sort of small things that you can change. As Sergei said, it's about the idea. And if you have a good idea and you believe in it, then you can get help. You can work together with people to make the application actually represent that idea well. But at least I wouldn't bother writing an application if I didn't really believe in it myself, which doesn't mean that it cannot be like safe, totally safe science. It has to be somehow like reaching for some sort of almost impossible things. But you have to kind of believe that this is a great idea.
Yeah, thanks. To add a little bit, who should apply? In my point of view, everybody who has this very good, excellent ideas. And also, it would be good to have CV which is good enough that at least the older you are, the more you need also to show that you have done something. In starting grant, this good idea very probably is enough, but in other grants you need to show that you have already achieved something, and that's why this good enough CV plus excellent idea. Why I have applied, of course, I need to keep people working in this area, employed, etc. This is one of the most motivation, but also it actually very nice or good to concentrate on writing a proposal. And also all those who are planning to write a proposal, it will take time. You cannot make it a day or two. It takes time to write ERC proposal. At least this my last one took around 500 hours, including those hours with people who commented it and helped me on that. It was more or less minimum this number of hours, and it's actually quite a lot. But I certainly would like more and more people to make the proposals. It's also a learning process. It's certainly not waste of the time. It's always good to learn also on not only on how to make a proposal, but also on your science. Somehow crystallize what you have in your mind to make a good proposal.
Okay, I think most of my things have already been said, but I'll just summarize. Why I applied, first of all, I needed the funding. And also, I had to in the sense that I didn't want to look back later and think that, oh, there was this great thing I could have applied for, but I just didn't do it. So it was there, I had to apply. And what I wanted from it, I think, well, I wanted to get the money. I wanted to be able to do my research, not only to employ myself, but to be able to do my idea exactly the way I wanted it. And I think the ERC was the only way that I could really do that. So it was a great possibility. And I think I also wanted to have the evaluation, because you say, if you have a great idea, if you believe in yourself, if you have a good CV, I wasn't sure if mine was good enough to be competitive with all these great researchers from all over Europe. So I applied in order to get the highest evaluation of how good my research was compared to everyone else, and if the idea was good. And that was one of the best things I got out of it. And I think, yeah, as Marco said, he was the first that mentioned it, I'm not quite as pro as Marco, so I spent several thousand hours writing my application, and also probably 1,000 hours preparing for the interview afterwards. So I definitely encourage everybody to do it, even if you have some doubts, because I had doubts, and I was very lucky to get it. But do not underestimate the time it takes to actually prepare. That's my best advice. Thanks.
Okay, thanks everyone. I think this was a very nice range of motivations, a variety of motivations from surviving to being able to pursue your own vision. Also, I think many people mentioned the freedom that this kind of instrument gives, the visibility And I think it was also very clear that this crystallization of your own idea, it's also beneficial for yourself to do it and to be able to communicate it to the others. And I would really agree with Hanna also that if it's clear to yourself why this is a good idea, that you believe, I think Annele also mentioned this idea, kind of believing in the idea, I think you have good chances of convincing the panel as well. You're often your own worst critic. I think maybe we can take, if there are some questions related to this topic, to kind of the motivation or who should apply. Are there some questions in the audience that came to your mind listening to these contributions? Yep.
So some of you have, or maybe all, I don't know, have tried several times before getting it. So what do you think you did differently in that time when you got it? Or was it just, what was the reason? Can you make it short in the microphone?
Yeah, we can.
Oh, yeah, sorry.
But if you now look this, I have applied the ERC 3 times. Once concept of ERC, this I didn't get. But this advanced grants 2 times and get both times.
Yeah, so Anna was asking what was different. This was actually a very important point that, you know, keep on trying even if you first time don't succeed. So Anna was asking this question of what the people who have applied several times and also got critical feedback, what did they do the next time round when they were successful?
Well, I think I applied for the pre-ERC, which wasn't, I didn't get that. Then I applied for ERC once or twice without getting it. And what did I do differently? I stood up earlier. I said, like, you know, I want to do this nice little science. And then in the applications that went through, I wanted to say that I'm going to be world's best. And that is just that, and it hurt, and I couldn't do it with myself only. I needed colleagues to help me to kind of say loud and clear that I want to be top of the world, and I can. And that's not, it feels a bit shit, but and it shouldn't be done in a distasteful way. We know examples of that as well, that the referees have said that this is too arrogant or something, but in my case it was clearly that I kind of was bold enough to say that this is big and this is top of the world.
Mm-hmm.
Well, what I to all who are writing proposals, I have one advice. You know, Einstein once said, if you, of course, he was a bit arrogant, but anyhow, he said that if you are not capable to explain to your mother-in-law what is the subject of your research, then it means that you're doing rubbish. Of course, he is too decisive, but what is a good idea is to try to explain in simple words what you are doing, and the simpler the better. And then it will be understandable, because you know that evaluators are not necessarily experts in your discipline, but good scientists. And so try to be understandable to everybody. This is difficult. This is indeed very difficult, but this is important.
So I applied only once, and I got the starting grant, and now I have another proposal in. So I have applied the consolidated grant, but I have no ideas what will be the outcome. So at the moment I can't reply to this question.
I also only applied once and I got it, but I would still like to really highlight this what was said earlier, that you need to have something you believe in, because especially in the starting and consolidated grants, you will be interviewed. And at that time, if you, on paper, you might actually be able to write down something you don't quite believe in and make it sound believable, but in the interview, you are really questioned on the topic. So it's worth at least really writing something you believe.
Yeah, I'm the lucky one who has lots of experience in interviews. So I can say, add to this that during the first interview, and I agree with Sergei that also the rejection, it was fair. I don't, I have nothing against it, because during my first interview and first application, I had some components in my application where I couldn't show my expertise, not on the paper or not in the interview. And based on the comments of the panel, especially on that topic, I just removed that part, that component, you know. It also made my work easier. And then, because in this panel is, every second year there is the same panel. Every other year the panel is different. So when I then, for the third time, went for the interview, that was the same panel as the first time, and I had carefully taken into account all the comments I got from the first round, and I think that was the key to success finally.
Well, I don't have this experience for getting a rejection the first time, but I was on the waiting list the first time, and only 2 days after I got the first rejection, I was invited for these negotiations. But I think it's not only about rejections from the ERC, you also get rejections from other projects, and it's also always important to get the message out of the reasons why it's been rejected, and this can help also for other projects. And in my special situation, this was the case in a national grant that was about the same category like ERC, but just Austria National Grant, starting grant for young scientists. But of course the budget is only half from ERC budget, so you could not propose the same amount of work that's been in the ERC. But in my situation, the deadline for the START grant in Austria was half a year before the ERC, and so I had to submit some pre-version of the ERC grant to the START grant, and obviously it was not good enough. But I got very important feedback from the reviewers why it's not acceptable for funding. And this information helped me a lot to improve really in detail the ERC grant.
Okay, thanks. So I think that, Nanne, do you have?
Yeah, I think I can add something.
Great.
So I also only have one experience with applying for ERC, and it somehow mysteriously went all the way through. But before that, I have quite a portfolio of rejections of other applications. And I think not so much did all the comments change my research, but it very much changed how I chose to present it to other people, because it made me aware of what is it that is difficult to understand in terms of why is it important and what is it that we're going to do and how. And the way I see it now is a bit like my proposal was this sculpture that was chipped out of wood, and every time I got this round of comments of people, and I would be really angry and thinking, like, how can they not understand this? This is the most obvious in the world, and then you realize, like, no, it's not, and then you start chipping more, and in the end, I think it became very clear, and I think it also crystallized something in the process to myself, which is very helpful now, because now I think the implementation goes smoothly, because I've had to explain so many times what is it we're going to do.
Thanks. Yeah, I think actually we've kind of indirectly got a lot of answers also to this question of what advice the grantees would give. And I think at least there has been the theme of listening to feedback, getting feedback and listening to feedback from colleagues and from evaluators. Thinking about the presentation. So thinking about how you present your idea so that you can convince the evaluators. But also, of course, deep down in there, you also have to believe. The first criterion is to believe in the idea yourself. Don't give up, and reserve enough time. I think that this cannot be stressed enough. But since we have still 10 minutes, I think I'd also would like to ask you one question that came up also from the audience during the break. So we have representation here from University of Vienna, Stockholm University, University of Helsinki, University of Eastern Finland, FMI and University of Oulu. So what I would like to hear, maybe we don't have time to go through all the candidates, but at least it would be nice to have, or panelists, but it would be nice to have a representative from all of these different organizations to comment on what kind of support you have got from your environment related to the grant, and what kind of support would you wish that the ERC grantees, when applying or when receiving the grant, would get. I think we have to be pretty brief now, but this was something that also came up.
Okay, so during the proposal writing phase, I got really nice comments, feedback, and support from the funding services. Ulrika sitting here. Thank you very much again. And when I was invited for the interview, I was in Oulu at that point, and I had the same experience from Oulu funding services that they helped me with some of the areas of preparing for the interview that were not my strong side, such as graphic layouts of the slides for the presentation at the interview. And then there was the Academy of Finland training, which was also extremely helpful. They had hired consulting agency that was also going through the proposals. And I think I would also want to stress the research environment. When you have this feeling that everyone around you actually also believe in your idea, and the activities of people around you also fit as complementary to your idea, you experience this synergy. And I think that feeling, taking that with me to the interview, was very helpful.
Thanks. Okay, so that was University of Oulu representation.
Also partly Helsinki,
Yeah.
I believe.
So who is it? Is it Markku who will talk for the Helsinki?
Actually say something what has been changing during these years. I think that in principle I have got all support what I have been asking. And in this first time in 2008 there was no consulting companies who was giving any help or something like that. And personally, I don't believe any consulting companies either. But actually, they gave me, Ulrika or somebody else gave me a nice bunch of papers, what I read, and I get a very good hints, which I think that were very crucial that I get over also the second time. Mm. And especially, I think that in the negotiations, etc., I have got a lot of help, and I think that it's pretty common. Mm.
I would say that the second time when I went to one of these advanced ERC course from this consulting company, and it was actually very useful because I knew the process very well and some things had changed. So I didn't have to read through that bunch of paper. I went there, I sat there 3 hours, and then I was ready to write. I didn't have to check what this means. And I mean 3 hours of listening to them and like points what should be in what section, and then after that I was like good to go. And I think that was very useful because it would have taken me a week to go through that bunch of papers, and I would have been bored and scared and what not. But that was useful.
Well, what I would say the most what is good from ERC in ERC. ERC invites us to distinguish and emphasizes the difference between how to say this revolutionary research and incremental research, but. This doesn't mean that we should consider incremental research as unnecessary. It's absolutely necessary. We are all we're learning first of all at university, and this is incremental activity, and then we need to know the language of science, and this is incremental, and that's why we need to this teaches us how to maintain balance between incremental part of what we are doing. So this is language of science first of all, and revolutionary this or how to say this
groundbreaking.
Yes, groundbreaking and like that. so, but it's a very recent initiative because nobody taught us at university to do groundbreaking. We learned how to do incremental, and we need to listen. What I'm summing up, we need to be happy when people criticize us, when we faced totally different views, which shocking us, and I think here all of you, all of us, has very good opportunity because of very international atmosphere. It's very important. So I came from Russia with a very strong school of turbulence, originated by Kolmogorov, and that are beautiful names. And I fully understand that if I would go on living in Russia and doing research, I would do it basically incremental. It's very difficult to get rid of the influence of your teachers. And that's why it's important to travel, important to listen to contradictory views, and to respect contradictory views. And this is, and I think ERC helping us to doing it.
Okay, so our university offered us a possibility to use the services of the consultant company. And I think that these services were helpful if I think about the technical issues related to writing the proposal and so forth. And also, of course, our research services offered lots of help related to technical questions like budgeting and so forth. But how I feel is that to get really help to polish your scientific content or highlight the importance of your groundbreaking research, for example, this kind of help is very difficult to get from consultant companies or research services. And I felt very strongly that the most important support I got from my colleagues, and also from my international colleagues and colleagues from other institutes. So I had lots of discussions related to my ideas and research topics with my colleagues. And I think that for me that was the most valuable support I got.
Okay.
Well, Helsinki was already. I just want to say that I got a lot of support from all the experience in this group on writing group proposals, and also the consulting company. It's not perfect, but I found I had a lot of use of that also.
Mm-hmm. Good thinking, Mikko.
University of Vienna is among the biggest universities in the German-speaking world. And we have about 90,000 students, and therefore there is also a big research service that's taking care of support regarding funding opportunities. So with respect to budgeting and so on, there was great support at the University of Vienna. Also, research service provided some kind of proofreading, correction for native English language corrections and so on. And this was also helpful because these guys are not from the subject, they just read what's written there, and they also need to somehow understand what it is about. So this is also quite interesting feedback. But very important for me was also getting feedback from colleagues, and they are from the subject, they know what it is about, and there is two categories basically. So one is colleagues who think this is excellent and they say perfect, but this is not helpful. And in this situation, I was very happy by providing this proposal to colleagues where you usually have some reservations because you're not on their own, you're not best friends with them. But if they criticize it, there is a reason. And this is criticism that's very helpful. And important is, don't take every criticism as it might be written down, but think whether this criticism makes sense. And only if you think for your own proposal this is a reasonable criticism, also take it. And that's the same for all the kinds of pre-information meetings where you get information how to apply for ERC and so on. They give you all kinds of advice on how you should do it. In the end, you have to decide how you do it, and that's then your own proposal.
Okay, thank you. I think our time starts to be up. I'll just ask a very brief last question, which no one of you need to say anything to, but just raise your hand. How many of you have received some extra money because of or related to your ERC grant?
What do you mean with extra money?
Support for, say, extra personnel,
Tämmöisiä bonuksia jostain.
like bonuses from the Finnish Academy, or because there are these kind of funding instruments to support. And I think I've at least received some. Okay, so about half and half. I think this is also maybe good for the audience.
Of
to
course,
know.
some of it is not called that,
No.
but in truth it is that.
Yes.
That-
And that's also good to be aware of.
I can actually add that I believe that with this whole that all of us we have got it. It's certainly one important part that we have the third period of Center of Excellence, for example. With being zero ERC by then, we would not get ever the third period of Center of Excellence in Finland. And then there are several other I also believe that some other support has been come via that.
And it is of course a concrete way for the environments to support the ERC grantees, and the ways also that the ERC will benefit you if you are successful. Okay, I think we need to start to wrap this discussion up, and I hope that this was useful for the audience. And I think one of the themes that now came up in this last section was ask for support and you will be given support. So I think everyone was saying that there is actually quite a lot of support available for the writing if you just approach the research services and your colleagues. But remember to give your colleagues enough time to read your proposal and react to it. So Hanna has some final remark.
No, I'm just saying that if you give me 2 weeks time and then after that 2 weeks it's 2 days to the deadline, do you think I'm motivated to give you comments if the comments are that you have to change the structure of your thing and complete the emphasis? You will not have time to do it. So it really is a really long time span if you want to take the comments into account, because that might take a month or 2 months to take them into account. So it isn't like 2 weeks is enough before the deadline, because then it's just wasted.
Okay, so I think that there is a clear message to remember to take enough time, and I think now we'll have to move on. We've taken too much time, 3 minutes over. So thanks everyone.
Okay, so thank you very much for inviting me to this ERC seminar today, and it reminds me of my own history, which after graduation started here in Helsinki with important funding from Marko Kulmala. So it's not only being one right decision getting to such a project, but also a sum of many different aspects that make the picture full in the end. So my ERC project is about experiments. So it's a break now from my pre-speakers, Hanna and Ilona, who were the modelers. Now it's going about experiments. And as you see from our logo, it's nanodynamite. It's basically a short composite of nanoparticle dynamics from high time resolution experiments. And now the focus of this is then how can we really describe the nanoparticle dynamics during this new particle formation events that we are frequently observing in the atmosphere. Now, what I wanted to point out here is the last two words, low signal. That's of course a certain relative term, meaning low in respect to the measurement technique. So you can go very low in concentration, like a condensation particle counter detects particles, single particles, or maybe tenth of a particle per cubic centimeter. But in the end, it's a question of technique, measurement technique that you're using. What's the sensitivity of this technique, and how low can you go in concentration to still get good signal? Now, we have mentioned already the ideas, and the idea for my ERC grant started in Boulder, it's in Colorado, during my postdoc, where I was working at NCAR together with Jim Smith. And I've just showing this picture from a particle formation event in the NCAR aerosol chamber, where we produced particle formation from alpha-pinene ozonolysis and using regular instrumentation. And you have seen these kind of banana plots already today. Nobody has talked about how these are measured, but in a way this also follows very straight to Hannah's second ERC grant. You identify a problem, you think about how is this thing actually measured, and then start thinking how can I improve this situation. So we see these particles form at some point in time. Of course, it's a laboratory experiment, doesn't relate to local time at all. But if you look at the y-axis, it's starting at 10 nanometers grayed out, and somewhere at 15 nanometers we start seeing some signal at some point. And I mean, I've of course I know the operation principle of a condensation particle counter, but I didn't understand why we don't see particles down to 10 nanometers with the instrumentation we were using. And so I was thinking, and how is this working, and talking to other people, and if someone also, other people cannot explain to you what's the problem here, then you might be on the right track. And so my idea was focusing really on the very beginning of this particle formation event, and if we do this, because this is where the particle formation actually starts happening. And if we focus in here on these sort of size distribution measurements, what we find that the SMPS is basically measuring an upscan and downscan, averaging and producing one size distribution from this. But in the very beginning of such a particle formation event, we see that the upscan and downscan differs by a factor of 5 or sometimes even an order of magnitude. So there is such high dynamics going on in these particle formation events that the instrument just does not capture the dynamics correctly. And that's a good situation, because then you know where you can improve things. Now, of course, this is a poor setup, 4 minutes time resolution, cutoff of the CPC is somewhere between 10 and 15 nanometers, so you wouldn't expect much better signals there. But if we improve the experiments and the instruments to analyze particle size distribution, we see basically the very same behavior. So this is from the cloud experiment, nano SMPS measurements operating at high time resolution. I don't know what's the exact time resolution, probably below 10 seconds per scan. And you see the light yellow area there starting at 5 to 6 nanometers. That's where the nano SMPS gets the nice signals. But below 5 nanometers, there is basically no signal at all. And then below 2 or 2.5 nanometers, there is the PSM again producing data on the size distribution. But there is evidently there is a gap in the sizing of the nanoparticles when they first start appearing. And there is, of course, a reason why this is happening, and that's related, first of all, to low counting statistics. So if you're scanning the voltage in the DMA, this does not necessarily mean that in the short time when you're at a certain size channel, you also have particles there, or if there are particles, they're just so rarely appearing that in the small period of time when this voltage is correct, there might not be a particle penetrating the DMA. And another thing is that preventing proper experimental characterization of the nanoparticles is the time resolution. As you have seen from the NCAR instrument, the regular SMPS has scan times of 4 minutes, and that's not sufficient to capture fast changing aerosols. And if we consider the PSM sizing information as the best information for the sub 2 nanometer size range, of course, everyone familiar with this technique knows that this sizing technique relies on calibration to certain artificial aerosol particles from the laboratory and does not necessarily respond in the same way for biogenic particles produced in the chamber or in the atmosphere. So for that reason, I designed a DMA train, what we call the DMA train. We produced the first prototype at NCAR with a number of DMAs taken from the TD SIMS and also some other DMAs from Pete McMurray's group, and tested this setup, and now we have a known instrument with using 6 DMAs in parallel and accordingly also 6 detectors for particles. And now the difference to the regular SMPS is we are not scanning the voltage and scanning with one DMA the size distribution over a certain time, but we have all 6 DMAs set to one fixed voltage and thereby to one particle size. And in a very narrow size range, let's say from 2 to 10 nanometers, we can basically cover the full size distribution between 2 and 10 nanometers by 6 independent DMAs monitoring at very constant conditions the size evolution of these particles. Now we have chargers where the particles that's sucked into the instrument are charged. Then we are sizing the particles in 6 DMAs and counting them. And this allows us to reach a time resolution in an ideal case of about 1 second. Not that ideal system, because if you consider that we have for the smallest size ranges also the PSMs that are have themselves already transmission time of about 5 seconds. So we're still below 5 seconds in regular operation. And with the setup, we are now able to cover the size range in the size range between 1.5 and 10 nanometers in very precise detail. This instrument is now published and was accepted last week by Atmospheric Measurement Techniques. Now, going back to the cloud chamber, here is the same figure I've shown before. Measurements shown from 2 different instruments. The bottom, smallest sizes from the PSM, and the upper one from the nano SMPS. And if we now add the DMA train data, we simply fill this gap and are now able to basically track the size evolution of the particles from the very beginning. Again, as Hannah pointed out, do we actually know what the experimental data tell us? How reliable is the data that we get from these things? And this is another point that motivated me to think more in an unusual way. How can we produce experimental data from nanoparticles? Because if we are pulling aerosol from the environment or from a chamber into our DMA train or SMPS, the aerosol gets extracted from its parent phase. So the particles that have just been formed from a certain chemical reaction and surrounded by vapors that allow the particles to form are suddenly removed from this environment and put into the sheath there of a DMA. So the environment for the particles suddenly changes completely, and we don't know what's actually happening to these particles in this situation. And of course, there's lots of inlet losses associated with the sampling. And an ideal solution to this problem would, of course, be optical detection. And of course, you know that the gas is not allowing the light to be transmitted at short wavelengths to really capture nanoparticles in an optical detection system. But the advantage of an optical detection system is, of course, you're measuring in situ. You don't have to remove the particles. And it also usually provides high time resolution. Now, the technique I identified as a suitable technique to start looking at the nanoparticles and their dynamics is using the small angle X-ray scattering technique. It's using X-rays, as the name says. It's an elastic scattering method, so you're not destroying the particles. And from the intensity signal that you're measuring from the X-ray scattering, this signal can be interpreted to obtain size and shape information. And it also provides a way to get a nice view on the average statistical representation of the particles. So it's not like a microscope where you look at individual particles, but you get a view on the average composition or structure of the particles. Now, the way this small angle X-ray scattering works, X-ray scattering works by the scattering on electrons. So you need to have electrons where the X-rays get scattered. And of course, any atom or molecule has electrons which can scatter the X-rays. And in an aerosol, that's a tricky task because the particles are surrounded by carrier gas, and of course, then you also have the scattering from the background. And if you compare nanoparticle concentrations of, if in a high concentrated aerosol, it's 10 to 6 per cc, but you have 10 to 19 per cc of gas molecules. So that's a critical issue in this study to get the background down. Here is a brief view on the experiment. We have a flow tube where we produce aerosol at the inlet, let it flow through, with the idea that we have a movable inlet that allows us to change the reaction time. And then we let the X-ray light through the flow tube and monitor the scattered lights. And of course, we need to separate this high vacuum from the X-ray beam line to the flow tube. And therefore, we are using Kapton windows. That's plastic material that's allowing the X-ray beam to penetrate these windows. And at the outlet, we are using conventional aerosol instruments to measure the regular aerosol size distribution. Now, this is how this looks at the beam line at the Lettra Synchrotron in Trieste. Here is our flow tube with the gas inlet and the aerosol. Here is our movable inlet that can be adjusted in position. Here comes the X-ray beam in. This is where the scattered signal goes out. And here is our regular particle analyzers. And without going into any detail here, this is how such an intensity curve from the X-ray beam looks like. And this Q vector basically gives you an inverse of the particle size. So low Q is large particles, and high Q is small particles. And if you look between red, blue, which is the intensity signal, and black is the background, there is very noisy signal, not much difference. And for that reason, we have replaced air now by helium. Looking at before the switching module, it's now pure air, and now if we go here to helium, it's still an aerosol. Of course, it's not an ambient relevant aerosol, but it allows us to get more into this detail. And if we now start looking into the change of signal between using air as carrier gas and helium, we see that the helium produces much less background, and this is what we need for our nanoparticles, which have very low scattering contrast. This funny bump at the end of the Q-axis is the characteristic scattering signal from the Kapton windows. So we know it's there, but we can also remove this by the proper data evaluation. And now if we look at the signal, if we add now the particles, the tungsten particles to this flow tube, we get a order of magnitude difference between the signal and the background. And that's the starting point after 3 years of research, when we now are able to start characterizing nanoparticles in situ from this SAX measurement technique. Okay, here are some conclusions. The DMA train has shown to provide important information in the 1.5 to 10 nanometer size range, and thereby fills an important gap that's not being captured by other instruments. And as I've just tried to motivate, we are now at the stage where we can use SAX to analyze nanoparticles in situ. And that's important. For that reason, it's important to use helium as carrier gas, because then we can reduce the scattering background from the carrier gas. And eventually, of course, we are trying to apply this method to biogenic particles. It's also been mentioned already, no research can be done without a very good research team, and thereby I want to also emphasize the importance of my group, which is proudly presented here. Thank you very much.
Thank you very much, Paul. I will have several questions, but I will ask them later. Okay, next talk by Annele, and after Annele's talk we will have a lunch break. And during lunch break, those people who have been invited to Actris meeting, we will go to Dynamicon, but not others.
Okay, so I will talk about my ERC starting grant project, Kappa. The project started 2014, so I still have about 2 years left with this project. And the project is concentrated on studying atmospheric organic aerosol particles, and especially their physical phase state. So I'm investigating whether atmospheric organic aerosols are solid or liquid. We published a paper in Nature 2010 showing that atmospheric organic aerosol particles can be amorphous solid or semi-solids. And this kind of paper was kind of the starting point of my ERC project. But in this study, we were not able to quantify the viscosity of the amorphous solids, amorphous solid particles, or we were not able to quantify the atmospheric implications of the physical phase state of these organic aerosols. So I could say that our paper left lots of open questions to scientific community. And with my ERC project, I'm aiming to reply to some of these questions. So I start with the short motivation part. So I'm telling you why I'm studying organic aerosols, what these organic aerosols are, and why I'm interested in physical phase state of these particles. So secondary organic aerosols are not emitted directly by certain sources to the atmosphere, but instead they are forming in the atmosphere from oxidation products of volatile organic compounds emitted by different sources. And these oxidation products, they have low enough vapor pressure so that the compounds can either condense onto the pre-existing aerosols or participate in the nucleation products, and hence new particles are forming in the atmosphere. So after the formation, these SOA particles go through different atmospheric processes, and for example, they interact with water vapor. And if the humidity is high enough, these particles can activate the cloud droplets. Hence, they affect on cloud formation and also cloud characteristics. And this is one of the reasons why we are interested in these particles. And I guess that you all are very familiar with this IPCC figure, so I'm not going too much into the details. But this figure clearly represents that the atmospheric aerosols have a cooling effect when the current climate is compared to the pre-industrial era. But what is also notable in this figure is the big uncertainties related to these cooling effects. And what we believe is that if we can understand the composition and properties of atmospheric aerosols well enough, we can decrease the uncertainties related to these cooling effects. And this is actually something that motivates my studies. So why I'm interested in physical phase state of the particles? So atmospheric organic aerosols are presented as a liquid droplets in models. So it's assumed that they are well mixed liquid kind of droplets. Now if the particles are semi-solids or solids having very high viscosity, that means that the diffusion limitations in particle bulk can restrict the movement of the molecules. So what does it then mean? It means that all the chemical reactions could take place only on the particle surface, for example. And also these diffusional limitations may affect on vapor uptake, meaning uptake of water vapor or organic vapors. So it is possible that the semi-solid or solid physical phase means that aerosols may have longer atmospheric lifetime, but on the other hand, they might be poorer cloud condensation nuclei than currently predicted by the models. But when the projects kind of started, it was clear that there were lots of questions related to these implications of the solid phase. But what was clear to us was that the viscosity of the particles was the key if we want to understand the atmospheric implications of our finding. So from this, we get to the viscosity of the amorphous material, and I like these illustrations a lot, so it kind of represents how much the viscosity of different kind of materials in the atmosphere can vary. In the left-hand side, we have, in the right-hand side, we have the liquid material having very low viscosity. And then when we are going to the left-hand side of the figure, we step to the area called semi-solids. But as you can see, the viscosity values of these semi-solids can vary a lot. If we are looking, for example, peanut butter type of semi-solid material, then the viscosity is around 1,000 Pascal seconds. But then if we go to the extreme, at the end of this line, we have glasses there, and the viscosity of these glasses is around 10 to 12 Pascal seconds. So when we are talking about semi-solids, we are really talking about huge range of viscosities. And what did we know when the project started? So based on our preliminary results, we were able to say that at least in some cases, the viscosity is higher than 10 to 4 Pascal seconds. But this was all that we knew. So that means that there were huge uncertainties still in the viscosity values, more than 8 orders of magnitude uncertainties. So to be able to define or quantify the viscosity of atmospheric organic aerosols and to answer to these several scientific questions that we had at hand when the project started, I built up the project with 3 work packages. In the work package 1, we are developing the new methodology to study or to quantify the viscosity of the organic aerosols. And this is very challenging because we are talking about very small particles smaller than 100 nanometers in size. And also the concentrations in the atmospheric conditions are typically very low. And when the project started, there were no methods by which we were able to quantify the viscosity of atmospheric particles. And then in work package 2, we take the methodology to the field or to the lab and quantify the viscosity and diffusion limitations in organic aerosols. And then we have also modeling work package 3, where we develop process modeling to describe how these diffusional limitations affect on different atmospheric processes. Okay, I still have about 2 years left with this project. So this is actually very active phase of the project. And at the moment, we, for example, have a measurement campaign going on in our lab to investigate some of these questions with the new methodology we have developed. But we have been lucky enough to get lots of interesting results, and I have chosen just a couple of examples here to show what we have found out by this far. So I will start with atmospheric observations, and then I will show some results on quantified viscosity values of organic aerosols. So in the project, we developed a very robust method to study whether particles are liquid or solid in their physical phase state, and the method is based on studying particle bounce characteristics. So we know that when the solid particles is impacting on solid surfaces, it bounces off from the surface. And if the liquid particles is impacting on the solid surface, it sticks on the surface. So this simple approach we took to the field, and we did measurements in Hyytiälä, in boreal forest conditions, and also in southeastern US in completely different conditions. In Hyytiälä, monoterpenes are dominating the VOC profiles, and also the ambient relative humidities are pretty low, typically higher than 40%. And in southeastern US, the isoprene is dominating the VOC profiles, and also the humidities are much higher, higher than 70%. What we found out was that in isoprene-dominated humid conditions, particles are mostly liquid in their physical phase state, and also we found out that the atmospheric oxidation further increases or further liquefies the particles. So we were able to conclude that in isoprene-rich environments where the humidities are high, the atmospheric organic aerosols can be treated as liquid droplets in the models. But when we are looking at Hyytiälä conditions, the story is a bit more complicated. So we can see that at lower humidities above 40%, particles are mostly semi-solid, and then they liquefy when humidity increases up to the 80%. So to really say how we should treat these particles in the models, we need to be able to quantify the viscosity of the particles. And for that, we developed several methodologies, and here is one example which I think is the most promising one. So the method is based on studying the evaporation characteristics of particles. So we have a new measurement method by which we can study the evaporation without increasing the temperature of the sample. And when we combine the experimental methods to the process modeling, we can get new information and quite detailed information about the viscosity of the particles during the evaporation. And here are some examples of our results. So here on the right-hand side, you can see how the viscosity of the particles is changing during the evaporation of the particles. So at the beginning of the evaporation, the values are much lower than in the end of the evaporation, where we have only very low volatility compounds left in the particle phase. And also, if we compare the viscosities defined at dry conditions or at 40% humidity conditions, we can see that there are clear differences. So the viscosities are about order of magnitude lower at atmospherically relevant humidity conditions. And what is nice about this methodology is that we don't get only information about the viscosity, but we also get information about the volatility of SOA components. And our results clearly show that a significant part of SOA components has very, very low volatilities. So what we can conclude from these results? So our results clearly demonstrate that at dry conditions, the evaporation is limited by the diffusional limitations in the particle bulk. But when we increase the humidities up to the values which are atmospherically relevant, the diffusional limitations plays only minor role in the process. And one of the reason why the diffusional limitations don't play a role is in the existence of very low volatility compounds. So in the atmospherically relevant humidity conditions, the low volatility of the SOA components is actually limiting the evaporation rate more than the diffusion limitations in the particle bulk. So what do we know about this viscosity at this moment? We know that at atmospherically relevant humidity conditions, the viscosities are in the range of 10 to 4 to 10 to 7 Pascal seconds, at least when we are investigating alpha pinene type of SOA particles. When we decrease the humidity, viscosity increases a lot, up to the values around 10 to 9 Pascal seconds. Then we have also results showing that when we further increase the oxidation state of the particles, we are increasing the viscosity of the particles. And at the moment, we are kind of trying to span this figure a bit so that we are also studying in our lab, actually, at the moment, we are studying how the temperature affects on diffusion limitation. So we can vary the temperature in the system as well. And then also we are investigating how the used VOC mixtures is affecting on diffusion limitations and viscosity values. And we are using, for example, real plant-emitted VOCs in our studies. Okay, so I think I'm running out of time, so it's time for acknowledgements. Thank you.
Thank you, Annele. And now I would like to thank all speakers in the morning session. We will continue at 1 o'clock, and now it's lunch break with own expense.
we'll continue, right? So, Mikael, go ahead.
All right, thank you. Nice to see so many made it back after the lunch break as well. So I took a slightly different approach to making my presentation than most of you have seen so far, and you can see it already from the title. I planned on choosing a title that would not confuse someone not from our field, but not using any complicated words. But having seen my title within the rest of the seminar program, I realized probably this equally confuses anyone within and without or outside our field. So, but Koala is indeed the acronym of the project, and the C does stand for comprehensive, and hopefully by the end of the talk you'll know why I highlighted that. So spelling it out, Koala stands for Comprehensive Molecular Characterization of Secondary Organic Aerosol Formation in the Atmosphere, and by now I hope that you've seen so many talks that you know what each of all these words mean. If you're wondering why I have a second slide which looks like a title slide and the version 2 on the bottom in the bottom corner, this is when working on the presentation for the interview in Brussels, this is what I had on my computer as version 2 as a title slide. This is what I had as version 6, which looks very similar to what my first slide was here now, except that here at least understood to write out the whole acronym, what Koala stands for. This is also what I brought to the Academy of Finland training event for the interview with the consultant firm, and coming back from there I realized that this was actually not a very good title slide, so I needed to make some amendments. This was version 11, and this was what I found the best solution in the end. The reason was that I realized that I needed one slide to kind of give an overview of my whole project, which I didn't have otherwise. So I kind of broke down the title, which is now on the top, into the orange part on the right, which is the secondary organic aerosol formation, which is the problem or the challenge or the question. And on the left, in the purple, is the comprehensive molecular characterization, which is then the solution of what we actually will do in the project. Now, on the right, you see that you have emissions, both biogenic and anthropogenic. They produce stuff into the atmosphere. Those tend to get oxidized in the atmosphere, and some of these oxidation products will prefer to go into the condensed phase and contribute to organic aerosol. Now, what we want to do in this project is to really comprehensively characterize on a molecular level this aerosol. And by now, there are a lot of instrumentation out there that we can measure the total amount of organic aerosol in the atmosphere, which is depicted by the total pie chart on the top. But these instruments give very little molecular level information. Luckily, there are other instruments like mass spectrometers that can also give molecular level information, but then again, they are unlikely to give the whole pie, but they will give some fraction, let's say 20%. And typical studies use one instrument, then they maybe get a very good molecular characterization of, let's say, 20% of the organic aerosol, which will be very useful. But if you want to plug it in a model, then you have to guess what the other 80% is. And as anyone can think, if you have to guess 80% of your input to the model, then the output will also probably not be very good. So the basic idea of this project was to use enough instrumentation to get all the pieces of the pie, and thereby get a full picture and not needing to guess anything. If you're wondering what my presentation in the interview was about, if it wasn't about talking about what I would do in my project, it was mainly about why the project would be important. So I made this kind of very rough, crude plots showing pre-industrial, present day, as it was when I went to Brussels, and then projection to the future. Pre-industrial, we had only biogenic natural emissions to the atmosphere. You can think of this as greenhouse gas emissions if you want. Present day, we have some anthropogenic sources on top of that, and then in 2100, if you're optimistic or pessimistic, we will have some anthropogenics also, but they might be more or less. And this I call now the emission uncertainty. What we as scientists then want to do is apply what we know and science to understand what the actual climate forcing is. So you can think of the y-axis then on top now as temperature or impact on temperature if you want. Pre-industrial, only biogenic, today. There is some anthropogenic on top of that. But as science always is, it's not perfect. So there are also quite big error bars or uncertainties in there. And as it turns out, a lot of these uncertainties due to aerosols, not all of it, but still for simplicity, if you extrapolate to 2100, you can get this kind of uncertainty that I then call the aerosol uncertainty. If we want to decrease this uncertainty in projecting the future, then one way to do it is that we start to make more and better measurements, and then we start to fit our models better and better to that. But the caveat here is that in this way, we can only decrease the present day uncertainty bar. We don't have a time machine to go do measurements in the past. So really, the only way to decrease both of these error bars is not by doing better and better measurements today, but actually understanding the detailed physics and chemistry behind the aerosol formation. This is also what Ilona talked about briefly also in her presentation. And to do this, well, that's where Koala comes in. The aim of Koala being that if we measure the physics or understand the physics and chemistry better, we will actually decrease both of these error bars, so 1750 and 2014, equally, and hopefully by the end of the project in 2020, not only due to the Koala project, but due to increased understanding, hopefully we'll have decreased both of these error bars enough to actually have a smaller aerosol uncertainty in 2100. And the way we plan to do this is deploying, like I said, enough different types of mass spectrometers in order to get the whole pie. And once we get all those pieces of the pie, then hopefully we will stop needing to make guesses and our uncertainties will become much smaller. Finally, I will talk a bit about the detail also what we now do, although I try to stay quite general until now. So we are limited by what we can measure. This is not taking anything away from people doing models or theory, but even the modelers and theoreticians do like to have some experimental data to compare their findings to as well. The way we want to increase what we can measure is by using, in this project, mass spectrometry, and more specifically chemical ionization mass spectrometry in a comprehensive way. As an example, I drew this plot, which was also a cruder version was in my ERC proposal as well. It shows now, starting from one of the major emissions, precursor emissions that actually form organic aerosol in the atmosphere, monoterpenes, a group of compounds that all have the chemical formula C10H16. Now, once these get oxidized in the atmosphere, just very crudely, we only add oxygen to this C10H16, which gives you the x-axis of that plot. So on the far left, we have just the monoterpenes with 0 oxygen, and then going from 1 to 10, we add just 1 more oxygen at a time. Now, if you add more oxygen, you also tend to decrease the volatility, and if you decrease the volatility, it becomes more likely to go into aerosol. So on the left, you have the blue part, shaded region, if you can see it, which are the volatile compounds, so they are very unlikely to be in the aerosol phase. In the middle, in the green, you have the semi-volatile, which can be found either in the aerosol phase or the gas phase. And to the far right, you have low volatile or extremely low volatile compounds that, once they find an aerosol particle, they will stick to it and not come off. The lines in this plot, again, show the estimated detection efficiency. It's not quite this easy, but let's say it is, that some instruments can measure different regions of this plot. So, for example, if we use H+, which is the furthest to the left, the solid line, it can only measure really the precursors and maybe with a few oxygens on. Then we have others that are completely insensitive to C10H16 without any oxygen, but then become more and more sensitive the more oxygen there is. The solid lines are instruments that we deploy quite frequently. The dashed lines are instruments that seem very promising, but are not, let's say, used to their full extent quite yet, because they still have some things that need to be worked out. But here you see that in order to measure all of this, we need different instruments to measure different parts of the pie in order to get the whole picture of everything on this range. If we focus now on the volatility bins here, then still, let's say 7 years ago, in 2010, there was quite clear consensus in the organic aerosol field that if you oxidized a certain monoterpene by oxidizing it by ozone, you get this kind of distribution of volatility. So most of the products are in the volatile region, and some are in the semi-volatile region, and the green parts of those bars is what is actually the aerosol part. Now, some years after that, very much a lot of Ilona's work also in models started to find that it doesn't really seem to make sense with our atmospheric observations. And in 2014, we actually found that the volatility distribution is probably looking more like this. So actually, probably most of the aerosol is probably low volatile instead of semi-volatile. And the reason we were able to find this was that we started deploying the purple line. So the furthest to the right, which is NO3-. We started using NO3- as a reagent ion in our chemical ionization mass spectrometers, and suddenly found that, hey, there's a lot of really highly oxidized stuff here that no one really thought was there beforehand. And if someone is saying, well, so what, just a small shift, the difference, if you, let's say, put it into a model, whether you say that your aerosol is semi-volatile or low volatile, it will make all the difference in the world for how that aerosol actually behaves. Not in the models, of course, only, but also in the actual atmosphere. And this was just before I started, or at the time, this was published when I started writing my ERC application. And this was kind of a starting point for the whole project, that now we can measure these really low volatile things, but all the heights of these different bars are still highly uncertain. We know it on a qualitative level, but not on a quantitative level. And therefore, the need for Koala, we need to be comprehensive. So the C stands for comprehensive. I didn't expect to have time for a summary slide, so I just end with thank you. And a comprehensive set of pictures of koalas. Thank you.
Thanks. To start a little bit later, there is possible one short question. So far there has been many. Okay, thanks. Maybe next time you could use one with the Lokapu gets also fun. And next is Hannele Korhonen.
Okay, thank you very much. I'm here to talk about my consolidated grant called ECLAIR. I totally remembered that I had ripped off Mikael's idea of the solution and the problem. I did not remember that I had ripped off the globe and also this blue bar on the top. So I think that I owe most of my funding actually to Mikael. Thanks a lot. So my project, this is trying to summarize again what it's about. It is dealing with aerosol cloud interactions in climate models, and especially trying to represent the things that are happening on the subgrid scale. And the reason why I decided to tackle this problem was that the current solutions that we have, the problem, they are either inaccurate but computationally fast, or then they are quite accurate but computationally slow. And what we're trying to develop here is a method that would be both accurate and fast, using some statistical emulation. I'm not going to explain this figure to this audience. I think that you all know what it's about, but I'm going to highlight two things. The first being that I only, in this project, look at the aerosol indirect effects and not the other aerosol effects. So that's the aerosol impacts on clouds. And the second thing is that we all know that it's very likely that the aerosol impacts on clouds have exerted a cooling impact on the climate, meaning that they have masked some of the warming from the greenhouse gases. But the big uncertainty means that we don't know by how much. And this means that there are large uncertainties related to the climate sensitivity, hence how much the climate will warm in the future when we keep putting more greenhouse gases in the atmosphere. So it causes significant uncertainties in the predictions of future climate. One of the main reasons, if not the main reasons, that there's such a large uncertainty in the aerosol indirect effect is that the interactions are very complex. We know that the aerosols modify the clouds in many ways. They modify the microphysics, the radiative properties, the lifetime, but also the dynamics like the thickness of the clouds and so on. But also the clouds modify the aerosols. So there's aqueous phase chemistry that modifies the composition and the size distribution. Wet removal is the most important mechanism by which aerosol is removed from the atmosphere, so it impacts the size distribution and number. And also there's transport, for example, in convective aftershocks, so that changes the layers at which the aerosol resides. And these all impact, well, firstly, their radiative properties, but also what is going to happen during the next cloud cycle. So these complex two-way interactions means that it's very difficult to constrain the aerosol indirect effect purely based on observations, because all the clouds and situations in the atmosphere are quite different. So it's difficult to generalize only based on observations. I do stress that observations are very, very important. So but this calls for some other ways to attack this problem as well. And I'm a modeler from the background, so I've tried to attack it with climate models. So what the atmospheric large-scale models, numerical models are trying to do is to put the best theoretical understanding that we have at the moment about the processes in physical, formulas, and then solve them numerically. Now, these models perform in many ways quite well. We can use them for lots of interesting science and projections. One specific restriction that they have when it comes to aerosol cloud interactions is, though, that the model resolution is typically very poor. So in current climate models, it can be something like 100 to 400 kilometers. And within this, let's say 100 times 100 kilometer grid box, all the quantities need to be averaged in a way, or then we have to assume something about their distribution. And we know that the aerosol cloud interactions take place on a much, much smaller scale. I've given some sort of examples of the spatial characteristics of cloud processes: deep convection, precipitation, scavenging some kilometers maybe, activation to cloud droplets, even micrometer size. So obviously there's a very fundamental gap between the scales of the models and what is actually happening in the atmosphere. And this means that the aerosol cloud interactions need to be highly parameterized, and in many cases they are poorly, if at all, represented in the models. Also, this fundamental scale difference means that it's very difficult to improve the climate models using conventional approaches. So we have to come up with something else. One thing that has been done is so-called superparameterization. It is also known as multi-scale model framework, MMF, which I think maybe describes it much better. But the idea here is that within each column, not only a grid cell, but each sort of a column of the global climate model, one runs a cloud resolving model, which has a much, much better resolution. It can capture many of the finer details of the aerosol cloud interactions. So what happens there is that this cloud resolving model is fed with boundary conditions from the climate model. It then runs and solves its more detailed information, and then feeds it back into the climate model, changing, for example, the temperature or the humidity tendencies. It has been shown that for aerosols, for example, it gives quite different results in some cases if you use the superparameterization or the conventional way. For example, it gives much more realistic cloud water response to aerosols than conventional models, so that it's closer to actually what is being observed. The problem with this is that it is very slow to run, as you can imagine. So it's about 2 to 3 orders of magnitude slower than the conventional model, and hence you can't use it for long climate projections. You can run it maybe for some years, but for the climate projections you want to run 100 years, and you want to have like several members in your ensemble. So in most cases it's impossible to use for climate projections. So what I proposed to do in this project then was to replace these cloud resolving models with emulators, which are statistical surrogates of the cloud resolving model. So the idea is that we will run, or we do run, the cloud resolving model, or large eddy simulation model in our case, offline for many, many times, and provide training data based on which we build a statistical model that we then hope to incorporate into the climate model. Now, I'm not going to go into the details of the techniques that we're using. There are many different ways that one could try and approach it. What we're using is a Gaussian process emulation. It's a Bayesian approach. But I think the main part there is that then our emulator doesn't only give you the mean function. It doesn't only predict like what is the likely thing to happen, but it also gives you an estimate of the uncertainty at the same time. And this can be very valuable in many cases. But basically what we hope that the emulator then does is that it will be fed with this information from the climate model, temperature profiles, humidity profiles, aerosol information, and so on, and it will give out some variables that are of interest to the climate model. It could be effective radius of the cloud droplets, cloud droplet number concentration, cloud optical thickness, and so on. Now that the emulators also give you the uncertainty, they can be used offline as well, not only within the climate model. They've been used, for example, in Ken Caslow's group in Leeds quite a lot for uncertainty analysis in global models, and that's something that we also hope to do. So we would also get information about what are the main uncertainties when we're trying to predict the aerosol cloud interactions on a cloud scale. I'm a little bit confused on how much time I have left, a couple of minutes maybe. So our project is divided into 3 work packages. In the first one, we are developing the cloud model of our choice, which is the UCLA LES model. And we are evaluating it against observations and then trying to develop it so that it gives us the best representation that we can possibly have what is happening with the aerosol cloud interactions in the atmosphere. In the second work package, we then built an emulator based on this cloud model, and we will also use it in a standalone mode for uncertainty analysis. And in the third work package, we plan to implement it into the climate model ECOM, then evaluate the new model against observations, and then also try and better constrain the aerosol indirect effect now and in the future. And throughout the project, we're hoping to use as much as possible experimental data to validate the model, but also use these modeling tools and these uncertainty analysis to feed back into the observational community so that we could point out the processes or the parameters that have the most uncertainty, and you as the measurement people should go and measure for us. I have currently 5 people working in this project, 2 postdocs and 3 PhD students. How much time do I have? 3 minutes. Okay, so I'll very briefly say something about these work packages. I think I've already said most of it, but the UCLA-less SALSA, UCLA-less SALSA as we call it, is maybe one of the most advanced in the world at the moment in terms of the detail of the aerosol cloud interaction description. So the actual large eddy simulation model has been developed elsewhere, but at FMI we have implemented a very detailed aerosol microphysical model, SALSA, into it. It's also quite heavy to run, but yeah, that's another story then. But in the first work package, as I said already, we're trying to construct the best possible description of the aerosol cloud interactions so that we can use that for emulation. We're mostly using here field campaign data to evaluate the model because there are the profiles are often available and measured, the surface fluxes are often measured and so on, so we have the most information from those measurements. But we can also use satellite data, and especially for the ice processes, laboratory observations. What we have done this far is that we have evaluated this model for several different environments. We have implemented ice-based processes, and they're currently being tested, but we have also made already quite a large number of training simulation data sets in a very iterative fashion for the proof of concept emulation. So the emulation work has started as well. I didn't initially think that trying to come up with a representative, good training simulation data set would be one of the big challenges of the project, but yeah, things surprise you. Maybe I'll skip that one. So in the second work package, as I said already, we have started that as well. We're trying to build the emulator there. I originally thought that this is going to be the riskiest part of the whole project, and it is in the sense that in order for you to build a good statistical representation, then the underlying functions, of course, need to behave somehow reasonably. But it looks now that, at least based on the data that we have, we can build reasonable emulators, the challenge being that the training data set needs to be very representative, and also how to actually then plug it into the climate model. But we have chosen a proof of concept approach here. So we're not trying to look at all the clouds in the world at the same time, but we first focusing on marine stratocumulus clouds because they're fairly simple, if you can say the clouds are simple, and there's also plenty of observational data there. And if this proof of concept approach is successful, then we aim to move for more complex cloud types. Here's an example of one of the first emulators that we built. Here's the simulated and emulated cloud fractions. At least in this case, the emulator seems to be able to capture the behavior quite well. Yeah, I won't go into the details with that. We haven't really started with the implementation work yet. I have 2 PhD students who have just started working in this project, but they are still learning to use the model. What we foresee at this point is that replacing some of the descriptions in the large-scale model, such as the cloud droplet number concentration parameterization, probably is quite straightforward because it is an individual parameterization there already. But if we want to replace some other parameters, such as describe the entrainment, it's probably going to be quite challenging because then we have to sort of get into the fundamental cloud scheme in the model. So we'll see how that goes. Yeah, I think that I'll just leave my summary slide up and put us back in time. Thank you very much.
Thank you, Hannele. And anybody think have a comment? Okay, we have quite good balance in this modeling and more experimental things with our ERC and also the information during panel discussion has been great. Okay, next one is Nönne.
Yeah, good afternoon, everyone, and I hope you're able to hang in there just a little bit longer. I'm the second last. My name is Nönne Prisle. I'm a former postdoc here at Helsinki University and currently leading the Atmos group in the Nano and Molecular Systems Research Unit at University of Oulu. My title, From Molecules to Future Rain, and so on, reflects the overall aims and research vision of my group. And my ERC project, Surface, is part of this overall vision. And as one of the last speakers, my project only began in beginning of March. So that means we don't really have that many results yet. I know expectations are incredibly high, as probably all the speakers. I received this email 45 minutes after my project started, Brussels time, asking me to please upload my results as soon as I would have some. But now 2 months later, we are still working on it. So in this talk, I'd like to talk about what we aim to do, why I think it's important, and how this idea evolved from my own work over the last decade. And then I'll describe some of the main resources we have at our disposal, our team, and the infrastructures that form the basis for the implementation of the project. So, in general, in my group, we're looking for signatures of molecular level processes on a global scale. And in Project Surface, we're specifically focusing on the processes that are taking place on the surface of nanoscale atmospheric aerosol particles and cloud droplets. And the way we're doing this is using a highly multidisciplinary approach where we're using both complementary experimental and computational methods and integrating processes such as, for example, aerosol formation and cloud droplet formation on a hierarchy of different scales reaching from the molecular level and to the global atmosphere. And why are we doing this? Why is it important? It has already been touched on by all the previous speakers. We know that climate is changing, mostly in ways that are not to our immediate benefit. So in order to do something about this, as we have just one Earth, we want to have the best possible understanding of the consequences of the different possible actions we could take. So aerosols affect climate directly from the scattering and reflection of incoming sunlight and outgoing heat, and indirectly through their critical role in the formation of cloud droplets in the atmosphere. And as we see in this iconic graph from the IPCC report, these aerosol effects still constitute the single largest source of uncertainty in our current best understanding of climate change and predictions of future climate. And some of the factors contributing to this is uncertainties related to the formation of aerosol in the atmosphere and their interactions with water leading to the subsequent formation of clouds. So, what I've learned from the decade of my own research before applying for the ERC is two critical things. One is that single molecular level properties have the potential to significantly affect overall aerosol processes and in turn impact aerosol effects on a global atmospheric scale. And second, evidence of which processes could potentially be key players in this has emerged from using new methods that have only been developed within the last decade. And one example of this is the case of surface tension, which is a critical parameter in the formation of cloud droplets. Many aerosol components are known to or speculated from their molecular structures, such as the one shown here, to be surface active in aqueous solution, like, for example, a cloud droplet. And this means that in the water, they concentrate in the surface, where they have the potential to reduce the surface tension compared to pure water. So, in my thesis work in Copenhagen 10 years ago, I measured the surfactant properties and cloud forming potential of a series of fatty acids as representative of marine organic aerosol. And then together with colleagues from FMI and University of Kuopio, we developed a thermodynamic model that allowed us to study detailed impact of surface activity on the aerosol processes. And with this, we made the first demonstration that surface activity of these fatty acids actually significantly impacts their cloud forming potential. But we also saw that the overall effect is not the result of a straightforward process, but rather complex interactions between different processes in the aerosol phase. So, after that, I proposed a simple way to represent the overall effect of surface activity on cloud forming potential in a way that was simple enough that we could implement it into a global climate model. And we did that together with colleagues from FMI. And with this work, we saw that how surface activity is represented on the molecular level can impact the predicted global radiative forcing and potentially by a magnitude that is comparable to that of CO2, the biggest driver of global warming. So, at the time, we did not have any experimental evidence of what was actually happening on the molecular level, because there was no way we could directly observe the surface tension of a single submicron cloud droplet or the surface partitioning as it would happen specifically in the droplet. But all of that changed when I learned about synchrotron-based X-ray photoelectron spectroscopy on a liquid microjet. So, X-ray photoelectron spectroscopy is a technique that's based on Einstein's photoelectric effect, where you shine an X-ray photon onto your sample, it kicks out an electron, which can then be detected. And we get then the binding energy of these electrons in their molecular orbitals as the difference between the energy of the incoming photon and the kinetic energy of the outgoing electron. And these binding energies are highly specific of the molecular species that they came from and the local chemical environment. And in addition, we know that X-rays can penetrate deep into matter, but the photoelectrons that are kicked out actually get scattered very quickly. So that means that only the ones from the surface layer can escape from the sample, and that makes the method very surface sensitive. There's still a catch though. When we want to study liquids, such as for example water and organics, representative of atmospheric aerosols and cloud droplets, these samples are highly volatile or semi-volatile. And this is not really compatible with these near vacuum conditions that we need in our system for the photoelectrons when they escape the sample to reach the detector. But this problem was solved 10 years ago, just about, by introducing the sample to the experimental chamber as a liquid microjet that travels so fast that it's continually renewed in the interaction region with the synchrotron radiation before it has the chance to evaporate. So in a sense, the liquid jet is like Lucky Luke being faster than its own shadow. So about 7 years ago, we did some of the first XPS experiments on atmospheric systems, using again a series of fatty acids representing the marine organic aerosol. And we were able to directly observe the surface active compounds in the surface of the water and the surface adsorption which causes it on the molecular level. In addition, we actually observed surface-specific chemistry that really surprised us, which is driven by the unique chemical environment of the surface and happens without any corresponding changes in the bulk. And we couldn't have predicted this from observing only bulk properties of our sample. So, as great as the liquid jet is, and it really is great, it's still a bulk system. So to maximize our atmospheric relevance of our experiments, we would like to look directly at aerosol particles and droplets during different stages of their formation and cloud activation. So together with colleagues from Uppsala and Lund universities some years ago, we took the initiative to develop an aerosol source where we can create aerosols or droplets using well-known techniques from aerosol technology and then focus them into a beam of particles or droplets, much like the liquid jet, through an aerodynamic lens. And these particles can then be studied in situ using synchrotron SPS. And in Oulu, at the same time, we've been developing the MUSCLE setup, which is a next generation cluster source that allows us to produce and introduce clusters, molecular clusters or nanoparticles into the synchrotron setup. And currently we are able to produce clusters with sizes from just a few molecules to a few thousand molecules, and composed of, in principle, anything from metals and salts to organics and water. There's still another catch here, and that as we go from a beam or from a liquid cylinder jet to a beam of particles or aerosols, our sample density decreases significantly. So in order to still see anything, we need to compensate this by increasing the photon flux to get a higher photoelectron flux, or by increasing our photoelectron detection efficiency. And we're currently working on both, but I would like to emphasize the unique role of the MAX4 laboratory, which just opened in Lund, Sweden last year, and is also referred to as the world's brightest synchrotron light source. So MAX4 is a synchrotron light facility that essentially produces very bright, coherent, and tunable light, mainly in the X-ray range. And this allows us to see very small things very clearly. So, for example, the surfaces of nanoscale atmospheric particles. So MAX4 is essentially a super microscope. And Finland is the second largest contributor to the MAX4 after Sweden. And our research unit is the Finnish national coordinator of all MAX4 activities. Together with the Estonians, we are building a beamline called Finest Beams, which is dedicated to atmospheric science as one of its main focal points. So this is a really unique opportunity for my project to be a part of. This beamline is more than 30 meters long. It's the number 8 on the schematic up there. And there's a cartoon of how it looks more in real life. It's basically coming to life now. It costs 10 million euros for the basic equipment and the staff during the construction, and another 1 million euro per year to run it. This has mainly been paid by Academy of Finland and from the EU. And then, to our most valuable resource, the team of people who each work on their own key part of the project and are bringing it all together as a team. So currently my research group has 5 members, and we, thanks to the ERC, are hoping to grow to 8 during just this year. First, of course, myself as head of group, I'm focusing on aerosol water and multiphase interactions, surface chemistry and thermodynamics, and on the multiscale integration. And then we have our theory whiz, Jussi. He's our expert in aerosol cluster thermodynamic, and his experimental counterpart, or nemesis, as you want to see it. And then Georgia is working on molecular level interactions in the aqueous phase, and then we have Sampo working on modeling of aerosol experiments. And to fill the gaps, during this year we hope also to employ an experimental surface scientist, an aerosol chamber experimentalist, and a climate modeler. And if you should be interested or know somebody who is, you can find the open positions that they are posted on our webpage. And of course, finally, we have excellent support and collaboration with the rest of the Nano and Molecular Systems unit in Oulu. In particular, the synchrotron radiation methods and applications group where they're focusing on developing synchrotron radiation sources and beamlines and instrumentation for nanoparticle research. So here at the beginning of my ERC, what I've learned so far is that in science, every question you resolve only leads to more questions that need to be answered. And my team and I are really excited to see where we will be in 5 years. Thanks.
Thank you, Nanne. Any questions? Yeah, I think that after Mikko I will not anymore ask.
You can always ask later.
Yeah. Last week is Mikko.
Thank you. So, I will say a few words about my very freshly started ERC project called Molecular Steps of Gas-to-Particle Conversion from Oxidation to Precursors, Clusters and Secondary Aerosol Particles. And because it only started a month or two ago, I obviously don't have any results yet to show. Instead, I will just describe you what is the basic concept of the project and what kind of preliminary data there is behind the project. So, as you have seen today, similar figures already several times today, in the atmosphere, certain volatile vapors emitted by anthropogenic or natural activities can be oxidized in the gas phase to form some kind of low vapor pressure aerosol precursor vapors, out of which few are known, but not necessarily all. Then these vapors in proper conditions, then they can stick to each other and form tiny little clusters in the size range of 1 to maybe 3 nanometers. And these clusters then grow by condensation and coagulation processes, or some of these clusters grow eventually to sizes of cloud condensation nuclei where they can modify cloud properties and thereby climate. And the gray circle in this process chain is now representing the core of this project. So I'm especially interested about the detailed molecular steps, how these clusters are formed, which are the chemical compounds associated to this cluster formation. After which I know which are the important precursor vapors. And if there is some questions that how these precursor vapors are formed in the gas phase, after that I'm interested also the oxidation mechanisms forming these precursor vapors. But there is even though this research question is super simple, I'm just asking that what are those molecules which are in these clusters around the globe. There cannot be more simple questions than that. But we have a big challenge, and the challenge is that concentrations of these clusters and also these precursor vapors, they are very, very low. And we are talking about concentrations far below 1 part per quadrillion. And because I want to experimentally detect and measure those, these kind of concentrations are anything but simple to detect. And if we put that in some kind of scale, you know that we have in the atmosphere, we have something like 10 to 19 molecules of air, nitrogen and oxygen in cubic centimeter of air. Then we have some other stuff like carbon dioxide and sulfur dioxide, 10 to 16, 10 to 10, and these are still concentrations that they are tools to detect these kind of levels. But then if we think about sulfuric acid, one of the most potential precursors of aerosol particles and those clusters, we may have something like 10 to 5 molecules per cubic centimeter, and that may be already sufficient to drive some new particle formation. And if we are talking about clusters per type, during new particle formation. For example, in boreal forest, we are talking about concentrations which are far below 1,000 per cubic centimeter. And that's the challenge what we need to face. And just you know, to give you some idea, the diameter of a human hair is something like 1 part per quadrillion of the distance between Earth and Sun. And this 1 part per quadrillion is now the present lowest detection limit of the tool, I believe, is the key eventually to solve the formation of these clusters and secondary aerosol, which is called chemical ionization, atmospheric pressure, interface time of flight mass spectrometer. The same tool as Mikael was talking about. And I'm not going into detail of this. I'm just saying that this is not yet enough. And therefore, in this project, work package number 1 is to develop new, more sensitive methods and improve the methodology and measurement technology what we have in our hands toward better sensitivity, better mass resolution, and so on, in order it to be suitable for solving these processes in complex atmospheric environments. After that, we are going to work in the lab, especially in Cloud CERN lab. This is not my lab, this is indeed Mikael's lab. So, but I needed just to have some lab picture there. And it's so fancy lab that I couldn't, you know, invent any better figure. But anyway, lab experiments allow us, in the atmosphere, when we measure whatever clusters or new particles, we don't exactly know what else is there in the atmosphere necessarily. In the lab, we know exactly what we are putting in. We can control all the conditions with high precision, and we can study how, from known starting point, we are producing new clusters and new particles. So they are important in that sense. But the final and most important part of the project is to really to resolve these cluster formation mechanisms, the molecules responsible on cluster formation and further growth in real atmospheres around the globe by direct mass spectrometric measurement. So that's the general idea what I want to do. And when I first time applied this grant, it was 2014, I think, something like that. Nobody had never measured in any atmospheric environment any cluster formation process on molecular level. And I didn't yet have, for example, this as a background data to show, to demonstrate, to panel that yes, we can do it. And this is now the first observation of neutral new particle formation, what we have been able to resolve in detail. So this measurement was made on the west coast of Ireland, where during low tide, this kind of macroalgae, laminaria, kelp stuff gets out of the seawater basically and gets in contact to air. It starts to emit all kind of iodine-containing vapors, which then, by some mechanism, are oxidized to something which was unknown, and then they form particles, you know, shown as the whitish, you know, apple-looking thing on the top of the figure. And simultaneously, what we can see is that we have some increase in sulfuric acid concentration, not too big, but it goes up to 10 to 6, the blue line. But we see that we have a much more pronounced increase in concentration of iodic acid, HiO3, the brown line. And we also see clusters made out of iodine oxides, red, bluish, and magenta line at the same time, you know, to come up. And if we look at the mass spectrum recorded during this new particle formation event, what we can see, well, first of all, x-axis, this is a very weird way to represent mass spectrum maybe, but x-axis shows the cluster mass. Every single dot in this spectrum is some kind of cluster with some certain composition. Y-axis is so-called mass defect, which is basically one of the ways to identify the atomic composition of these clusters, so that we know out of which molecules or atoms those clusters are made. But anyway, you don't need to think of it too much. The important thing is what we can see is that we first start with iodic acid molecule. Then we add another iodic acid molecule. We lose water, and there is some intramolecular restructuring reaction forming I2O5. Then we add once again iodic acid, once again, da 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 da, and eventually our mass range ends at 2200 or something like that, and we still see these neutral clusters made out of mostly iodic acid. And this is now the first demonstration that resolving these cluster formation mechanisms is kind of theoretically somehow possible. Still, we don't know where this iodic acid comes from. And this is now the chemistry part. We find that iodic acid makes the clusters, but nobody in this world doesn't know or can explain yet how iodic acid forms in the gas phase. So that's the stuff with which we are now very efficiently working with. The second explanation, example is from Antarctic. We measured, we were there in 2014, 2015, spent there one local summer, and we saw lots of new particle formation. And there, when new particle formation occurred, we saw some iodic acid, yes, we saw methane sulfonic acid and stuff like that, but the most pronounced increase was with sulfuric acid. We saw high concentrations of sulfuric acid. And indicating that here, instead of iodic acid, sulfuric acid plays a role. And what we find, this is the similar figure as earlier, except that this is from naturally charged ion clusters. So these are ions, not neutrals. And what we see here is this leftmost red dot is bisulfate ion. Then there is sulfuric acid adding on top of that, another sulfuric acid, da 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 da. The red dots are pure sulfuric acid clusters. Blue dots are sulfuric acid ammonia clusters. And for example, very high up there, 8 to 6 means there is 8 molecules of sulfuric acid, 6 molecules of ammonia. And this, together with some other data which I'm not going to show here, shows that the new particle formation mechanism in Antarctica is sulfuric acid ammonia ion-mediated nuclease. And once again, open questions emerge. Where does the ammonia come from? We don't yet know. And it seems that it's 2 o'clock. I will stop here. But anyway, the goals for the next 5 years is to resolve this cluster formation pathways in variety of atmospheric environments around the globe. We will solve the nature and origin of these precursor vapors, including the chemistry associated in formation of those, such as iodic acid. And we also want to focus on initial growth mechanisms. You know, how those clusters grow, which are the compounds growing the clusters toward cloud condensation nucleus sizes. We also hope that the instrument development will provide new tools for the scientific community outside our group. And of course, we hope that these results will end up at some point to global models and so on in order to improve the prediction capability of those models. So thank you very much. That's it.
Thanks.
No question, Mikko.
Yeah, I promise. Could have some questions. Okay, we have now heard all these ERC awareness talks during this morning and afternoon. We had very nice panel discussion. Hopefully also we had some hints for those who are now going to apply in near future in some ERC. I still would like to encourage everybody to apply. Of course, those who are not yet doctors and those have not yet been 2 years postdoc to get a possibility to get a starting grants. Mikko has some comment.
Yeah, I have one comment on this encouragement of applying, because ERC, if they reject, they put you in the category A, B or C, and you better to have a good application to end up to category C, category A, if you reject. Otherwise you get careless, you cannot apply next year or you cannot apply next 2 years. So I still suggest that once you write your application, you have some kind of confidence that you are going to be funded. So no point to submit a very poor application, because then you are in category C.
Yeah, this is actually the case what everybody need to consider, that which kind of risks one take in those applications. This encouraging everybody means also that of course everybody need to think it beforehand. When you're like Nönne said that she has think all her career, her idea, and now she received the ERC grant. I can also say that also I have do this kind towards this direction, but I have got those ERCs all my career in a way or other. It takes time. But on the other hand, don't be too worried about getting this kind of punishment. For example, if you are waiting whole time that you are sure that you get it, you never will apply. There is always risk, at least in my case. The biggest risk was that I have got typically 2 kinds of reviews. Somebody saying that it's my business as usual, that I will anyhow do it, or then nobody can do it. And there is some window between that, where we try to hit in that window to get in, and that's why it's a complex situation. And now Hanna's comment before I will close finally that.
Well, I'm thinking about all that is that I heard and what I've seen before. It is often that you mix a new methodology to a problem that it hasn't been applied for before. So if, I mean, in very many of these it's something like there is a new fairly well-established methodology on another field or developing methodology, and then you apply it to another thing. Or like in Hanne's case, you know you take this emulator thing to solve it from a completely different kind of angle. The thing it's the same. You know, it was for me originally this making this quantum chemistry for the clusters rather than thermodynamics. So if there is that sort of element, that should, I think, encourage you to that this might be a good basis for the application.
Yeah. And of course for the younger ones it's important to find out that when you develop your CV you start to have enough independence to show that you are publishing without your supervisors once in a while, and especially during postdoc period that you start to get this kind of independence. This is one one important part. And of course, one what in my point of view is very, very important is that it takes time. You need to make proposals, you need to use the time for writing proposals, not only ERC proposals, but other proposals. And maybe somebody is very clever or very lucky and get it with short period, but at least I'm not that clever or that lucky. And also what was said by, for example, by Sergei, is that it's also good to get reactions. Couple of years ago, I started to get reactions with almost all proposals what I made, and then I need to somehow revisit my basic ideas and basic ways of doing it. And all this kind of making something new that you cannot really continue, or if you want to get the second one or third one, you cannot really continue always in the way. And of course there has been the discussions about the synergy grants, if they are really coming after a year or two. And we should be eyes open that when they are coming. The synergy grants are actually, you know it. Yes, which time of 2018 is the deadline?
There has been various information, both that will be already in the end of this year and then early next year.
Mm.
So that it will open will come to 2018.
And this is of course. Yes. Yes.
I learned a lot during this seminar today, and I'm just inviting people to think about. So I understand that these very small-scale processes, which are in focus, made basically during today, with on the way from gases to nanoparticles, low particles, and cloud. Some of these processes, obviously clustering in particular, should obviously be affected by turbulence. And I am just informing you that new knowledge of turbulence is totally different with what, essentially different atmospheric turbulence compared to what people were thinking about turbulence only a decade ago. And we are now in a position to predict or to calculate small-scale turbulence, which is controlled by the dissipation, much more accurately. And if it is important for this kind of processes, then very welcome to speak to me. So then perhaps it could be a subject of a project or even of one of the issues in Synergy project. Very welcome.
Thank you, Sergei. This is what I mean, that it would be good if we also get some synergy project. And maybe when we have ERC 20 years anniversary, we might have much more of these ERCs. I do not see any reason why our group or our Center of Excellence, why we would not get more and more of those in future. We are in principle doing quite many things right in that, and hopefully it will continue. And one important thing what is that we still have critical environment inside the group, which is in my point of view quite important. Like Paul Winkler said in his presentation, that it's good to get critical comments. Although, let's say some kind of feelings point of view, they are not nice to have, but in this kind of science point of view, they are very, very crucial and important to have. And let's keep this critical environment, what at least in my point of view has been around me whole my career in way or other. And I don't even know that how I can manage if there is not critical people around enough. They are very, very valuable. Okay, thanks to everybody and thanks to all audience and participants. And waiting for next proposals to comment for.